Thank you very much. I'm honored to receive this award, and it's my pleasure to have a block lecture here. I would like to talk about our studies on steel research by atom probe. The title is Application of Atom Probe Tomography to Steel and Hydrogen Analysis. This is our outline of my talk. First of all, I will show you the needs for atom probe tomography in steel industry and problems of atom probe for the steel application for introduction. And next, I will show you some improvement issue for steel application. And then I will talk about the atom probe application to several fundamental issues of steel. And finally, I will show you the atomic scale hydrogen visualization and summarize my talk. This figure shows a production process of cold rolled thin steel sheet in hot rolling steel process. The worked steel undergo recovery, recrystallization, and transformation, resulting in the partitioning, precipitation, and segregation of the aluminum element. In cold rolling process, the worked steel also undergo recovery and recrystallization. Such a metallurgical phenomena controlled by heat treatment and addition of suitable aluminum element for obtain the desired microstructure. So we have to understand the true state and the true behavior of aluminum element in steel, by using in actual production process by using atom probe. And for the reduction of carbon dioxide, higher performance steel are required. For example, with high strength and high ductility, with which are conflicting property. Steel is an inhomogeneous materials with various kind of phases and defects. As the figure shows the influence of the phases and defect on each steel property. It's necessary to understand the exact relation between the microstructure and mechanical property by multi-scale characterization for obtaining the distinct material design. Atom probe is used as the ultimate analysis tool. Our laboratory introduced a three-dimensional atom probe, so-called 3DAP, from Oxford Nanoscience in early 2000 for steel research. The equipment has a field ion microscope system, FIM. The atom probe can detect every element, including light elements such as carbon, boron, hydrogen, with a high spatial resolution. However, there are several problems for scale application. First, the analysis region was very small, less than 1 or 200 nanometers from the tip apex. So site-specific tip preparation from the target positions in the homogeneous materials was needed. At that time, focused ion beam film fabrication was already conducted, but without sampling was not still applied to the atom probe specimen. Secondly, atom probe has less ability in crystallographic analysis. So we applied the FIM analysis. Thirdly, quantitativeness of atom probe, the quantitativeness of an element had not been investigated sufficiently. So we elucidate the mechanism that degrade quantitativeness through some experiment. in next section, I talk about the improvement of these problems. This is our first trial using F5 lift-up method, whose target is a triple junction Glenn boundary. Okay? Such a trial was performed before the introduction of this equipment. A few years later, a site-specific specimen tip preparation was established like this. A small pillar block was lifted out on the needle stage, and sharp tip, including a target position, was fabricated on the upper part of the block by figure mirroring. However, an unusual phenomenon was observed, in which field evaporation didn't occur even in a sufficient voltage application. By the numerical calculation of the tip field, we understood that the field factor strongly depends on the shape of around tip. This figure shows the calculation result of field factor as a function of the tip length and block diameter. To realize a low field factor, the tip length should be longer than the twice of the block diameter. It was our initial guideline for tip fabrication. And these are examples of site-specific tip preparation and atom probe analysis. This is an observation of the bainite ferrite interface. The interface was identified in a SIM image of edge surface. We observed partitioning and segregation of copper and molybdenum across the interface. And this is the observation of the interface between the micrometer-sized oxide inclusion and material ferrite. Oxide inclusion are effectively used as a nucleation site of ashkelonite. And we revealed that several oxide thin layers with a different composition stuck on the oxide layer, oxide core. And we also applied the site-specific tip preparation to heavily non-aperitic steel wire. The micro shows that the fine ferrite lamella elongate parallel to the drawing direction. Conventional analysis of the wire was performed along the elongating lamella because the specimen tip was prepared by the electropolishing of the thin wire directly. Our proposed analysis is a measurement across the lamella by preparing the specimen tip perpendicular to the lamella. Because this resolution of atom probe is much higher than the lateral resolution. And this is a comparison between the two measurements, parallel and perpendicular to the elongating lamella. In our proposed analysis, you can see several concentric rings with a bright and dark contrast in the final image, corresponding to the ferrite and cementite lamella. And multi-lamellar structure is clearly observed in the carbon. The concentration profile suggests our proposed analysis shows more accurate carbon concentration in the thin lamellar cementite. And the conventional analysis tend to overestimate the cementite decomposition. The measurement direction of atom is a very important factor for analysis of thin lamella or boundary. And to make up for this ability of atom in crystallographic analysis, we effectively use FIM analysis. This figure shows a Glenn boundary characterization using FIM pole fitting method. these are affine images of a Grain boundary in low carbon steel. The boundary position is identified as a dark band. The left figure is a pole fitting of to grain A this side, and right figure to grain B this side. Okay, from the two grain fitting, the misorientation angle and rotation axis of the boundary are calculated for several minutes. So this method can be used in situ during the experiment. And furthermore, using the affine pole fitting and atom probe result, we can determine grain boundary plane orientation. And these are atom map of iron and carbon and their concentration profile across the boundary by calculating the rotation matrix of the boundary to the reference plane in the map. The grain boundary plane normal in a needle coordinate system is obtained. The angle between the rotation axis and the boundary plane normal is about 30 degrees. It means the tilt component of the boundary is 30 degrees and the twist component is 77 degrees. So this grain boundary is revealed to be the mixed boundary with a large twist component. And finally, by transformation into a crystalline coordinate system, grain boundary plane normal to the two grain are plotted in an orientation map like this. One of the boundary plane is near 1, 2, 2 orientation. Using the affine pole fitting method, we can obtain the macroscopic 5 degrees of freedom of the grain boundary. Okay, so next I talk about the quantitative performance of atom probe in the analysis of iron element in steel. Okay, this figure shows the temperature dependence of the appearance concentration of various solute elements in ferrite iron under the low frequency condition. Okay, the deviation from the real concentration becomes larger with increasing the specimen tip. Solute titanium and silicon increase, whereas solute copper decrease with the temperature. Okay, as a result of qualitatively explained by the preferential evaporation and rotation. Okay, the diagram shows the evaporation field of copper and silicon in an iron matrix. Copper has a lower evaporation field, whereas silicon has a higher than iron. At a high temperature, copper atoms preferentially evaporate during the DC voltage application, whereas silicon atom retains on the tip surface, okay, even in a pulse voltage application. Atom probe detect a pulse evaporation ion only, so the apparent concentration shows a different value from the real one. And we propose a quantitative physical model describing the preferential evaporation and retention. This model assumes the presence of the homogeneous surface layer with a different concentration in the tip, and the surface concentration are periodically changed by the pulse and the DC voltage evaporation. The change in the surface concentration arises from the evaporation difference in evaporation probability between the iron element and the matrix iron. Okay? Two mass balance equation of the iron element concentration are written here. We define the three physical parameters like this. Parameter A is related to the evaporation rate. Okay, B is related to the activation energy of iron and iron element, and C is related to that of the only iron. Using this parameter, okay, the experimental result was fitted Okay, as a figure shows experimental result of apparent kappa concentration and Windows noise relation, as a function of the temperature in iron 1.2 atomic percent solute kappa alloy. The apparent concentration and background noise were simultaneously fitted well using suitable parameter. From the fitting, DC evaporation ratio was estimated. You can see DC evaporation drastically increased from the about 70 Kelvin. This figure shows the experimental result of appearance silicon concentration in iron 6.3 atomic percent solute silicon alloy. We can use the same value, for parameter A and C, because they are related to the only ion. And parameter B is related to the activation energy of silicon. So by choosing B equal to 1.2, good consensus was obtained. The calculation result indicates that influence of preferential retention on appearance concentration is smaller than that of the preferential evaporation. Using our proposed model, we can quantitatively understand preferential evaporation and retention of the iron element in steel. And carbon and nitrogen is the most important element in steel because they strongly impact microstructure formation and mechanical property. However, quantitative performance has been unclear. We investigate them using stoichiometric samples, Fe3C cementite and Fe4N nitride. Cementite has exactly 25 atomic percent carbon, and nitride, this nitride has mostly 20 atomic percent nitrogen, from the phase diagram. The nitride sample was produced by plasma nitride using 14 nitrogen gas and isotope 15 nitrogen gas, because molecular nitrogen ions N2 plus at the 28 Dalton might be hidden by the main ion peak. First, I show the cementite analysis result in voltage. The 24 Dalton peak is composed of dimer and tetramer carbon ions. Therefore, mean carbon number of ions at 24 Dalton was estimated from the peak ratio, 24 and 24.5 Dalton, using this equation. This is the result, and this is the assignment 1. The apparent carbon concentration shows much higher than the 25 atomic percent with a large temperature dependence. The deviation is considered to be arise from the detection loss of matrix ion. As the assignment 2, the detection loss was corrected based on the Miyamoto reference, Miyamoto paper. And then the almost correct carbon concentration without temperature dependence was obtained. On the other hand, in beta mode, the mean carbon number at the 24 Dalton was quite large, and the apparent concentration was nearly 25 atomic percent carbon, only using assignment 1. It means that the detection loss of the matrix ion is very small in a beta mode, probably because tip heating reduces the co-evaporation of the ion with a near distance on the tip. for the quantitative analysis of carbon in voltage mode, both the mean carbon number and detection loss should be considered. Whereas in the laser mode, only the mean carbon number at the 24 Dalton is needed. And next, I show you the nitride analysis result in a voltage mode. You can see nitrogen is detected as N plus and FeN plus ions. The apparent nitrogen concentration was much lower than the real composition at 20 Kelvin and further decrease with the temperature. Okay. According to the previous report, the nitrogen deficiency corresponds to the N plus ions, okay, at 28 Dalton hidden by the ion peak. Okay. In order to avoid the mass interference, the isotope 15 nitride was observed. Okay, this is a comparison in the mass spectra between the 40 nitride and 50 nitride. The 50 nitride clearly shows the N plus ions and at 15 Dalton and N plus ion at 50 Dalton and N2 plus ion at 30 Dalton. However, even including the N2 plus ion, the apparent nitrogen concentration was much lower than the real composition. This missing nitrogen increased with the temperature. The same result was obtained in the laser mode. The origin of the missing nitrogen is predicted to be the occurrence of neutral nitride or nitrogen gas molecule in a field evaporation. And these experiments revealed that the quantitative analysis of carbon in steel is possible, but that of nitrogen in steel is currently impossible. I submit this study using the isotope nitride in tomorrow's poster session. Okay, so next I talk about the atom probe application to several fundamental issues of steels. Okay, particle strengthening by titanium carbide, vanadium carbide, nickel carbide, and copper precipitate is widely used for high tensile steels. However, strength mechanism of these particles has remained unclear. We investigate them by estimating interaction force to dislocation of particle. This figure shows a schematic diagram represent the particle diameter dependence on the interaction force due to the various strengthening mechanisms for copper precipitation steel. In misfit effect, there are drop when the coherence is lost. In chemical effect, the force is almost constant, independent of the diameter. In elastic modulus effect, the force steeply increases in the small diameter region and then gradually increases. In friction force effect, the force linearly increases with the particle diameter. According to the dislocation pinning model, the interaction force can be estimated from the critical shear stress and mean particle spacing using this equation, which are experimentally derived from the tensor test and atom probe analysis. This figure shows a copper atom map of iron 1.2 atomic percent copper alloy with a various aging time at 500 degrees C and the amount of the particle strengthening by a tensor test. You can see a copper cluster homogeneously generated for 0.5 hour aging, and they grow up with prolonged aging time, particle diameter increase and number density decrease. The blue arrow indicates peak aging region from the peak mean particle diameter and number density of the copper precipitate. The mean particle spacing was obtained for each aging. And this figure shows estimated interaction force per kappa particle as a function of the mean particle diameter. The force steeply increases in small diameter region, but does not drop when the coherence is lost, which suggests that a contribution of the misfit strain effect and the chemical effect are very small, much small. And the interaction force is well fitted by the elastic models model proposed by Russell and Brown, with a reasonable parameter. Therefore, the strenuous mechanism of kappa particle is mainly elastic models effect and not the misfit strain effect. On the other hand, the result of titanium carbide precipitation scale is represented in the same figure. The interaction force of titanium carbide is larger than that of the kappa particle in a small diameter region, which indicates titanium carbide is a stronger particle for dislocation. The strenuous mechanism of titanium carbide is considered to be the friction force effect because of the linear relation with a particle diameter. So next, since a segregation state of at the grain boundaries in high temperature austenite phase influence phase transformation during the cooling in steel. The observation of prior austenite grain boundary in water quenched martensite was very important. However, it was difficult to prepare the specimen because martensite has a high number density of the boundary, such as the last block packet in addition to the austenite grain boundary. We developed the specimen preparation method for a prior austenite grain boundary by the combined use of EBSD, TM, and film. These figures shows the transmission EBSD result of the specimen tip just before the atom block measure. There's austenite, prior austenite grain boundary here, and this is the block boundary and packet boundary. Here's the atom map shows the molybdenum and the boron, and segregate the prior austenite grain boundary only. And using this method, we investigate the relation between the segregation amount and the hardenability in the molybdenum boron combined additions. In interaction excess, interfacial excess of molybdenum, only molybdenum and only boron, and molybdenum plus boron, appropriate in the graph, of segregation amount and hardenability index. The hardenability index is linearly related to the interfacial excess of molybdenum plus boron. Therefore, the hardenability is determined by the austenite grain boundary concentration of molybdenum boron. The effect on the hardenability per unit segregation atom is almost the same between the two elements, which implies the hardenability improvement by molybdenum and boron segregation is the same mechanism, probably reduction of austenite grain boundary. And the next issue is dislocation segregation of a substitution of solid atom. Niobium addition, significantly better the recovery in steel, but it has been unclear whether as solute niobium or precipitate niobium litters recovery, we observed a segregation of niobium atom to dislocation in a niobium added ferrite stainless steel for high temperature use. We call it the niobium Cottrell atmosphere, and the interaction energy between the niobium atom and edge dissolved core was estimated to be about 40 kilojoule per mole. This is evidence that the solute niobium causes retardation of recovery at a high temperature. So finally, I talk about atomic scale hydrogen visualization in scale. The hydrogen embrittlement become more serious and higher strength scale. Hydrogen penetrate from the surface, diffused into the steel, then aggregate at the lattice defect and strength field, and cause a destruction. As a hydrogen embrittlement mechanism, these are four hypotheses are proposed. For the first one, hydrogen directly weakens the bonding of the bond. And for the others, hydrogen influence behavior of the defect, such as dislocation and vacancy, and indirectly cause embrittlement. To obtain the material design with a high resistance to hydrogen, it's necessary to understand the hydrogen trapping site and the hydrogen behavior in steel. However, direct observation of hydrogen in steel was very difficult by using conventional analysis method. So, atom probe is expected for the atomic scale hydrogen visualization. And so, in hydrogen observation using atom probe, we have a critical problem. Background hydrogen noise, H plus, always appears during the measurement, and behind the actual hydrogen in steel. This figure shows a change in the hydrogen noise concentration depending on the pulse frequency at the same detection rate per pulse in voltage. The concentration increase with the decrease the pulse frequency, which indicates the residual hydrogen gas in the analysis chamber absorbed on the tip surface during the sending voltage and will evaporate like a constituent atoms by pulse voltage application. Hydrogen noise also depends on the crystallographic surface and phases, so it's impossible to avoid the hydrogen noise completely. In order to distinguish the actual hydrogen from the noise hydrogen, like performs hydrogen isotope to tell you a charge to the specimen tip before measurement. And for the observation of hydrogen trapping site, we first consider the behavior of hydrogen atom in near surface region of the tip, because atom probe observed just the surface region of the tip. This is the energy diagram of the hydrogen in hydrogen atom. If hydrogen atom at the trapping site detrap and diffuse for only 50 nanometer, the charged hydrogen at the trapping site easily escape from the surface. Hydrogen diffusion is very large, even at the measurement temperature. This figure shows a calculated detrapping time of trapped hydrogen from the trapping site with various trapping energy as a function of the temperature. You can see detraps easily occur at the room temperature, even if the trapping energy is quite large. In contrast, detrap never occur at the measurement temperature, even if the trapping energy is very small. Based on the calculation result, we are sure detrap deuterium atoms at the trapping site would be visualized if charged deuterium could be left in the tip surface region after charging. So we designed deuterium charge cell, which enable deuterium gas charge inside the equipment by local heating of the specimen tip in deuterium atmosphere in order to overcome the surface barrier, and rapid cooling of the tip just after the charge in order to prevent the charged deuterium from escaping. Okay, and this is a temperature profile for charging process. After deuterium charge at 300 degrees C, the charged specimen tip was rapidly cooled and transferred to the analysis chamber. And I show you the observation result of titanium carbide precipitation steel. Solute treated steel was this composition was water quenched and annealed for precipitation. This is hydrogen desorption, hydrogen thermal desorption analysis. TDA profile of the quenched and annealed steels. The large peak at about 2000 degrees C is a hydrogen trapped by the titanium carbide precipitate. We observed this trapped hydrogen. Okay, and so the trapping site associated with the carbide precipitate, such as the titanium carbide, vanadium carbide, nickel carbide, has remained unclear. As a hypothesis for trapping site, trapping field, broad interface, and the edge interface were inside the platelet has been proposed. Okay, this figure shows atom probe result of deuterium charged and uncharged specimen tip of the titanium carbide precipitation steel. Titanium and the deuterium atom position are represented here. The titanium enriched region corresponds to the nano-sized titanium carbide. A distinct correlation was observed between the deuterium and titanium carbide precipitate in deuterium charged specimen, whereas such a correlation was not observed for uncharged specimen. Okay, these three sets of the figure show the front and side view of each platelet in a 10 nanometer selected cubic box. You can see deuterium atoms are homogeneously distributed on both broad interface of the platelet, okay, and not the edge interface. Therefore, we conclude the main hydrogen trapping site is the broad interface of titanium carbide platelet. We assumed that the origin of the deep trapping site is either missed dislocation core at the interface or carbon vacancy at the carbide surface. To find out which of the two is correct, we studied a vanadium carbide model scale with a slightly larger carbide precipitate observable by TM. And this is a change in yield strength of the vanadium carbide model scale with various aging time. And this figure shows Titan TDA analysis result of the steel. The amount of trapped hydrogen increased with the aging time to tell the peak aging and degrees in overaging. The desorption temperature is shifted between the under aging and peak aging. And by Cho and Lee method, the trapped energy was estimated to be 25 kilojoule per mole for under-aging scale and 60 kilojoule per mole for peak and over-aging scale. The difference in trapping energy suggests that the hydrogen trapping state associated with the vanadium carbide was changed by something related to the precipitate itself. Okay, this figure shows the atom probe result of deuterium charge specimen tip of 4-hour under aging scale with a small trapping energy, and 8-hour peak aged scale with a large trapping energy. No deuterium atom were observed around the platelet in under aged state like this. Okay, the concentration profile indicates that it has nearly VC compression. In contrast, a lot of deuterium atoms were observed along the broad interface of the platelet in a peak aged state. Okay, the concentration profile indicates it has nearly V4C3 composition. Okay, which means presence of carbon vacancies in the platelet. Okay, this figure shows a magnified maps of iron and deuterium in a direction parallel and perpendicular to the platelet in a peak aged state. The low 4 figures are 3 nanometer thick sliced atom. You can see most of the deuterium are distributed near the 001 broad interface and not inside of the platelet. Okay, so this figure shows a high resolution image of the precipitate in under aged state and the peak aged state. The broad plane of vanadium carbide platelet is along the 001 plane, which has a Baker-Nutting orientation relation with the ferrite matrix. Okay, a white arrow indicates the identified dislocation. As shown before, a lot of deuterium atoms actually observed on the interface in a peak age state, this state. Okay, however, only a few dislocations observed on the coherent broad interface in the both of two states. Therefore, the origin of the deep trapping site is not misfit dislocation core. Okay, so our co-author report by first principle calculation, carbon vacancy within the V4C3 have a large trapping energy, okay, but they are huge diffusion value, which suggests hydrogen cannot diffuse inside the precipitate. Therefore, we conclude that the origin of the hydrogen trapping site is a surface carbon vacancy in the coherent 001 broad interface of V4C3. We also consider deep trapping site of titanium carbide and nylon carbide also have the same origin as a vanadium carbide, because such a carbide precipitate also contains a carbon vacancy analysis by the composition analysis of the atom. Okay, so in summary, a very short summary, with some improvement for the application, atom probe, atom probe has been effectively applied to the steel industry. In addition, direct observation of the hydrogen in steel become possible by deuterium charging method. Okay. However, we must not forget that the atom probe data contains many artifacts due to the local magnification effect, evaporation, ablation, field-induced vibration, mass interference, and several types of noise, especially hydrogen noise. It's necessary to understand the mechanism and to solve these problems. Finally, I would like to sincerely thank to all my co-author. Thank you for your attention. Okay.
Thank you, Yoon, for this excellent presentation. It was very, very interesting. Probably we've got time for questions. So is there any question in the audience? So we've got Julie Carney. Julie, can you talk?
Thank you so much for presentation.
We can't hear you, Julie. Your sound is not good.
Can you hear me now?
Yeah, better.
I'm sorry. Sorry about that. I just wanted to say thank you for such a beautiful lecture. Really enjoyed it. I especially love your results where you used the 15 nitrogen to look at the nitrated samples, and also very interesting to see that there's still such a big deficiency in the nitrogen even at low temperatures, which I think you said you attribute to neutrals. I guess my question is, that's probably the case, but why do we see an increase in the number of neutrals that form at higher temperatures? Any thoughts on that?
Okay. Okay. This figure. And so, okay. I submit this work to tomorrow's poster. And okay, the idea, okay, maybe okay, the missing nitrogens is come from the neutral nitrogen or nitrogen gas molecule. So in that case, temperature is important factor. Some activation energy or something. I don't know, but I guess now.
Okay, well, thank you very much.
Discuss a poster session, okay, if possible. Okay.
Okay, we've got a question of Lee Stephenson. Lee?
Hello, can you hear me?
Yes, perfect.
That was a great talk. Thank you very much. I'm sorry to have missed the first 10 slides. I had some other work that I was struggling to finish here on Australian time. My question relates to what your views might be over different hydrogen charging routes people have in the past, in contemporary research, they're using electrolytic charging with various solutions and also plasma charging. Do you have any views on those?
You mentioned about the method of deuterium charging. Okay.
Yes, electrolytic charging and plasma charging.
Okay. Unfortunately, I didn't try plasma charging. Okay, but okay, I say about the merit of charging process, charging method, and gas charge is I think better because okay, needle tip keep the clean, you know, and but it's hard to hard to make a special chamber in atom flow. And
yeah, I agree.
Yeah. The most people use the charging, deuterium charging using a solution, and okay, and it's easy, but we have to check the contamination of the needle tip. Okay, and if possible, I try to the plasma charge in the future.
Yeah, I would see that as very interesting. It's in that case, you've just got to jump over the safety hurdles that, of course, are present with gas charging also, and have the right equipment. All right, thank you very much, Professor.
Okay. You've got a question from Arun Devaraj. Arun?
Can you hear me?
You can hear you.
Okay.
We can.
Good talk. Thank you. So my question is, after you do this high temperature gaseous charging, does it matter how quickly you transfer the sample from that chamber to the atom probe analysis chamber? Was that a variable that you changed in terms of how fast do you transfer, and does that change the results? That was the question.
Okay, so I didn't catch your question, but okay, maybe you already have the high temperature charges, 300 degrees C in our style. And okay, okay, so yeah. You mean the cooling?
Yes. Yeah. Once you charge it, how quickly do you have to cool it?
Okay.
Does that matter?
Okay. Okay. It's a very important point. Okay, so I made the patent of this system, and in my case, that it's okay. And in my case, I use cooling system of liquid nitrogen, you know.
Okay.
And okay, in my style, okay, so first the specimen tip was cooled by liquid nitrogen to heat conductivity, and so increase the temperature by heating only tip apex region only.
Okay, interesting.
And okay, quit the heating, and the suddenly the temperature decrease.
Okay.
Yeah.
Okay. Very interesting. Okay. Is that published about your design, or is there any information on what?
Yeah. Yes.
Okay.
I write my first paper.
Okay. Fantastic. Okay. Thanks. We'll look at it.
Okay. Thank you, Arun. I've got a last question. I think it will be the last question for you, Yoon. You did your charging with electropolish or FIB or focused ion beam preparation when you do your charging. I just want to know if there is any difference if you charge an electropolish tip or an focused ion beam prepared tip.
Yeah. I use both specimen tip.
And did you see the difference? No difference.
No difference. And okay. In my style, every needle tip was checked by the FIM image, and after that I charged the deuterium. So if the image is bad, so I quit the specimen tip. Okay, so there are no difference.
No difference.
Yes.
Perfect. So thank you again, Yoon, for your very great talk. We are really pleased to have you today. And I would like to have this clap from everybody, but it's not possible. Thank you again.
Okay, thank you.
I think Yong, you can open your speaker now. You can take charge of the following session.
Okay, yeah. Okay, good morning, everybody. My name is Ronghu. It's a great honor to be the chair of this session of structural materials in this morning. So we have 3 speakers for the first half of this session. The first one is Professor Gang Xia from Nanjing University of Science and Technology. And the topic is segregation, desegregation, green boundaries of ferrite, iron, manganese, silicon, steel under ion radiation. So I will hand it over to Professor Xia, and you can start now.
Okay. Let's start. Okay. Oh no, that's wrong. Sorry. What's this one? I got this one. Okay. Can you see my screen? Can you see my screen?
Yes.
Okay.
Yes, we can see you. It's okay.
Okay.
Yep.
Okay, and now I start my talks. The title of my talk is Segregation and Desegregation at Green Boundaries of Ferritic Steels under ion irradiation. And I gave this talk on behalf of Qi Chen, a professor, a master student of my group, also Shen Baojin, and also Rong Hu. She currently moved to the University of Technology of Nanjing to start up her own research groups. Okay, so we all know the ferritic steel have very important in nuclear power industries, in particular in pressure vessel steel applications, because it's an important component for safe operation of nuclear power stations. The significant research interest to look at the irradiation damage on those type of steels. A lot of research has been conducted on the industrial steels with very complex compositions. Like this one, there are so many components. The difficulty is with such a complex compositions, it's very hard to understand the pair interactions or ternary interactions for the damage formations. Also, Professor research has focused on the damage in the matrix, such as the clustering formations, dislocation loops, and vacancy, as well as the interstitial type of defects. And they observed with the increase the irradiation dose, and they are strengthening effects. Also, they are low ductilities. So it's called the irradiation-induced embrittlement. And the materials we are investigated, we want to look at simple systems, and we want to explore the binary effects in those alloy systems. Also, we interested what happens is green boundaries. And the irradiation dose we are looking at up to 1.5 dPa. It should be long-time exposure in the real irradiation conditions. So the effect we are interested in, first, the effect of ion irradiations on the alloy element segregations and precipitation at green boundaries. Second, we want to look at the effect of pair interactions of different alloy element on green boundary segregations. And thirdly, we are interested to look at the effect of green boundary characteristics on the green boundary segregations, such as the high angle green boundary, the low angle green boundary, as well as special green boundaries. So the materials we are looking at is a model alloy, very simple system. It's a ternary alloy. It's have 1.3% manganese content and 0.2% of silicon. The rest of elements such as carbon and phosphorus and copper at their impurity level. We conduct ion irradiation experiment at 3 energy level to create a plateau irradiation damage zones within the depth of about 80 nanometers from the surface. With such uniform irradiation damage zones, we can easily take samples with the same irradiation damage to make our investigation easier. Also, we use the EBSD to check all the green boundaries. We found that it's for the sigma 3 green boundaries, it's only 7.2% of lines fractions, and the majority is high angle green boundaries, about 93%. And there are some low angle green boundaries, only 6.8%. So here is the stream simulation results about the damage distributions in the depths of the specimen. So with those specimens, we also can evaluate the strengthening effect of those alloys. Okay, here is a typical green boundaries we investigate. We investigate specimen in unirradiated conditions. Also, we look at the specimen in the irradiation conditions. And we look at 3 types of green boundaries that we can easily identify from the EBSD maps. Then we make the tip sample with the fake, and finally we got the green boundary successfully. And this is the irradiation sample, which also selected the similar type of sigma 3 green boundaries, also low angle green boundaries for analysis. Also, we can look at the high angle green boundary as well. So with those EBSD information, also item proof informations, we can work out the characteristic of each green boundaries. This is the unirradiated samples, and we can work out the misorientation of those 3 types of green boundaries. Also, we can work out the rotation axis as well as the green boundary planes for each greens. So that's the comprehensive information for each green boundaries we analyzed. So here is what we obtained for the sigma 3 green boundaries with and without irradiations. So for the unirradiated samples, this is the green boundaries viewed in adjunct directions, and this is the green boundaries viewed along the green normal directions. So you can see there are 2 parallel dislocations, marking this is not a perfect sigma 3 green boundaries, just slightly misorientation to the distortion from the perfect sigma 3s. And by measure the concentration distributions across these dislocations, or away these dislocations, like in the region 1 and in the region 2 regions. And we can see there are strong magnetic segregations when the region across the dislocations, and there's slightly enrichment of carbon as well. If we pick the regions without the dislocations, we can clearly see that there's segregation of also the manganese and much stronger carbon as well. And if we look at the overall green boundary regions consist of the dislocations, also the without the dislocations, we can clearly see the solid segregation levels of the different elements. After irradiations, also we can clearly see that there is dislocations with much stronger magnetic segregations, but surprisingly, and there is no carbon segregation in the green boundaries. So that is when you across the dislocations, or you just overall the green boundary areas, you cannot detect any clear segregation of carbon. So after the irradiation, the segregation disappeared of the carbon. Then we look at the low angle green boundaries. For this is the unirradiated samples. It consists of a lot of parallel dislocations. Also, we look at the 1D concentration profiles. We can see the fluctuation of the manganese concentrations corresponding to the enrichment of each dislocations. But the carbon segregations seems not showing any consistency with the correlation with the dislocations. That is the overall segregation along those green boundary measurement. We can see there's strong carbon segregation as well as silicon segregation, manganese segregations developed at those low angle green boundaries. And this after irradiations, still we can see the parallel dislocations. Also, we can see the dislocation with the enrichment of manganese Also, we can see the slightly silicon enrichment. If we look at the overall green boundary segregations, we can clearly see the manganese segregations, also the silicon segregations. Again, it is low angle green boundaries without proper segregation. So we look at the high angle green boundaries. This is the unirradiated samples, and we can see there are strong manganese segregations, also much stronger carbon segregations. There are certain silicon segregation as well. But for the irradiated samples, we can see the significant drop of the carbon content segregation levels. Also, the enhanced manganese segregations. So in order to evaluate those segregations, we use the solid size, measure the different green boundaries. Here is the results I listed in this table. You can clearly see the influence of green boundary characteristics, such as misorientation angles on the segregation of each element. You can see a clear influence on the manganese segregations, also clear influence on the effect on the carbon segregations. And the rest is pretty weak. So we want to explore the correlations between the different elements, such as the manganese and the silicon interactions, by the have certain interaction to influence segregations. If we plot all the data points, we see there are no clear correlations between the manganese excess to the silicon excess. It's almost horizontal distributed. And those gray point is we can find the data in the literature from the different industrial alloys, very complex industrial alloys. And if we look at the carbon concentration excess with the manganese excess, there is clear correlations for the unirradiated samples. That means with the increase of manganese segregation, carbon segregation also increased. But under the irradiations, this correlation was completely destroyed. We only can see a slightly carbon segregations. It is high angle green boundaries. So we also looked at the green boundaries, observed that under the irradiation, there's a manganese-rich precipitate from on the green boundaries. The size is about 10 nanometers. If we look at the program, we can see the core of the precipitate, manganese-rich precipitate, can reach about nearly 50% of manganese. And within those precipitates, there is no clear segregation of the carbons, very, very weak partitioning of the silicon. So here is the results we plot in a different way. This is the unirradiated samples and for the different green boundaries, and we look at the solid size. You can clearly see the correlations between the carbon and the manganese. And if we look at the irradiated samples, we can see the enhanced manganese segregations compared to unirradiated samples. Also, we can see the desegregation of the carbons from the green boundaries. Because this alloy is only have very low carbon concentrations, that means there is no carbon precipitated from this alloy. So we really want to know, so where those magnesium come from to the green boundary segregations and where the carbon goes. So we just measure the compositions, 15 nanometer close to the green boundaries. And here we can observe there's a difference between the unirradiated samples and the irradiated samples in the manganese concentrations. That means with the increase of irradiation, the manganese concentration with this region decrease. And we can see the enhanced carbon concentration within the 15 nanometers, further away from these green boundaries. Also, we can see the carbon concentration difference. And in the irradiated samples, the carbon concentration increase. Also, there's a manganese concentration decrease as well. So that clearly tells us how the diffusion happens. But what drives these diffusions? That's what we are interested in. What drives the carbon depletions? So our understanding is different from the provide assumption that always consider the growth of carbide cause the depletion of carbons. But we think that is due to the irradiation caused the interstitial manganese as a double segregated to the green boundaries and repel the carbon out from the green boundaries. Also due to the high vacancy implanted into the matrix and increase the carbon solubilities, and as a result, and so the carbon diffuse back to the matrix. So here is a conclusion we can get. So with the atom probe, really we can get a new insight into the carbon segregations behaviors under the ion irradiations. Also, we can understand the pair interactions of these alloys. So I think I will not read all the conclusions. I just thank you for your attention.
Hey, thank you very much, Professor Xia. It's a very good timing. So we probably can take 1 minute for a quick question. Yes, anyone has a quick question? So if not, then if anybody has question, can contact Professor Xia later to have a detailed discussion. Okay, thank you very much. And
thank you.
So, thank you. So our next speaker is from Qingqiang Ren from Oak Ridge. The topic today is the understanding the influence of boron in additive manufactured cobalt nickel-based superalloy using atom tomography. Okay, Qingqiang, you can start now.
Oh, hello everybody. My name is Qingqiang, or QQ to save some trouble for English native speakers. Today, on behalf of all my co-authors, I'm presenting our work entitled Understanding the Influence of Boron in Additively Manufactured Cobalt Nickel-Based Superalloys using atom tomography. Before I start, I'd like to first acknowledge the funding agency, US DOE Advanced Manufacturing Office, our collaborators at Carpenter Technology and the University of California, Santa Barbara, the user facilities, MDF and CNMS at Oak Ridge National Lab. A special thank you note to James Burns for his help with sample preparation and experimental running. So additive manufacturing is playing a bigger and bigger role in some mission critical structural components. And if you look at a typical AM process, here is an example of a laser power bed fusion technique. And if you look at the melt pool, what it's going through is a really complex thermal cycle. The laser beam will hit the melt pool rapidly, and it will rapidly cooling and then heating up again and cooling, heating, cooling, etc. Such complex thermal cycles makes it really vulnerable to all kinds of welding cracks. So basically, until today, most of the AM community, they are focusing on alloys that is weldable. Non-weldable alloys is still considered not printable, with maybe a couple of exceptions. And one element that's known to increase cracking is boron. It's well documented in the welding literature that too much boron can cause cracking. It has a very strong segregation tendency, which where it segregates, it will reduce the solid liquid interfacial energy, which is really bad for the previous thermal cycle I mentioned. And however, in the meanwhile, boron is actually a common beneficial minor element in superalloys. And by segregating to green boundary and forming different borides there, it basically stabilizes the green boundary and can improve the creep resistance. So basically, we want boron to achieve act as a green boundary strengthened and does not want it to introduce cracking. So the question comes, how much boron is the right amount and it's not too much for AM process? So the current study, we are trying to understand the role of boron played in these two additively manufactured cobalt nickel based superalloy. We label one of them as a low boron grade, which has 0.08 atomic percent of a boron. For the high boron grade, we double that, so we have 0.16 atomic percent of a boron. Please note that for any 0.08 is almost the highest boron content you can find in any commercial cast superalloys. So basically, we are trying to understand the role of boron at the high end of it. By the way, those two alloys are actually commercially available. Let's look at the as printed microstructure. So if you compare with the same printing parameters, if you compare the left and the right, higher boron grade has way more serious cracking issue. So more boron almost equals more cracks. And I should note that with further optimization with the printing parameters, even this small number of cracks can be reduced. But for this study and the mechanism understanding, we still use these two samples for further. Here are three green boundaries we observed in the low boron grade. Obviously, boron segregates at the green boundary, and for this green boundary too, and we also see a couple of tantalum carbides that's pinning the green boundary. When you look at the compositional profile, well, boron is the element of interest here. It shows a very strong segregation behavior at the green boundary, way stronger than all the rest of the elements. And the peak concentration, boron concentration is about 0.7 for this this green boundary. And for the other two of them, if you look at that, the compositional profile is almost identical. So the peak boron concentration is quite similar. And we also try to use Gibson access to compare the results quantitatively. For those who are not familiar with this, Gibson access is basically how many number of atoms are in excess due to the process of interface per unit area. So the results are presented here for the peak boron concentration, like the average is about 0.77, and Gibson access of boron is about 3.8 atom per nanometer square. And very small variations were observed here, although we randomly select these three green boundaries. So we think it still reflects the nature of the sample. Then let's turn to the high boron grade. Here's a fib cross section with the high boron grade. And this is the cracking. We just cross section among here to look at the typical cracking morphology. As you can see, the morphology can be rather complex, so which will be a challenge when we're trying to get the surface of these cracks. And also there's another crack appearing here. So basically the interspacing between cracks is about 20 micrometer. So it would be really hard for us to avoid to get a region that's far away from cracking. We get 2 atom probe tips from the cracked and the uncracked green boundary one in the high boron grade. They are about 5 micrometer away from each other. So here it's a reconstruction. Very obviously, boron is enriched at both uncracked and the cracked green boundary. And if you look at the compositional profile, we have an even stronger boron segregation behavior at the uncracked green boundary. If in comparison with the low boron grade, what we get for the peak boron concentration is about 1.5 atomic percent. When you look at the cracked region with this green boundary, the boron concentration is even higher. What we reach is about 2 0.0 atomic percent peak boron concentration. So we also convert that to Gibson excess, and if we would wish that's the whole story, and here what we get is like high boron grade, almost double the boron at grain boundary. So we double the nominal boron concentration, we get more boron at the grain boundary, and also the correct grain boundary showed even higher boron. So that probably makes sense. However, there's always a but. So this is not the complete story. Here are two other grain boundaries observed in the same sample, high boron grade, and what the computational profile tells us here, like the peak boron concentration is way higher, that even more than the correct grain boundary we just saw. The peak boron concentration is about 8.5. And for another grain boundary for this same sample, it's not as high as 8.5, but what we get is still 4.5. So it's still higher than the correct region of the grain boundary. So basically, high boron content itself maybe does not mean cracking itself. The orientation of the misorientation of the grain boundary and maybe local environment also matters in the cracking formation. So to summarize everything, if we started to additively manufactured cobalt nickel based silver alloy, and one with high boron concentration, one with the low boron concentration, what we get is the grain boundaries in the high boron grade consistently have more boron than the grain boundaries in the low boron grade. So you input more, you get more. And for the same grain boundary in the high boron grade, the correct region have more boron than the incorrect region. Okay, that kind of really links the boron content with the cracking, but when you look at the other two incorrect grain boundary, it has significantly more boron, even more than correct region, correct grain boundary. So boron content itself does not directly lead to cracking. So we will also consider the misorientation of grain boundaries as a part of the future work. Okay. Thank you for your attention. If any question, I'd like to address any questions or comments.
Thank you very much, Xintian, for the good timing and a nice work. And is there any questions? Okay, I probably have one question for you. And okay. So do you think the observed boron segregation behavior, do you think it has any connections with the grain boundary misorientation?
Yes, I think it will strongly, like the energy of the grain boundary is different as the variation of the misorientation. So that will play a big part for cracking formation. Actually, we will focus on that for future work.
Okay, yeah, thank you. Okay, so if there's no question, then we'll move on to our next speaker. Thank you very much, Xintian. Thank you. So our next speaker is Jia Liu from PNL, and her topic today is the microstructure and mechanical properties of friction consolidated oxide suspension strength steel. Okay, Jia, probably you can start.
Okay, hello everyone. So today I'm going to talk about the microstructure and the mechanical property of friction consolidated oxide dispersion strengthened steel, like ODS steel. So here's the list of the authors or collaborators who run across like 5 different institutes and working on the same project. So ODS steel is a promising structural material for fusion reactors. The high density of high stable yttrium titanium oxygen nanooxides provide high sink strength for radiation resistance and high temperature creep strength. Here I'm talking about greater than 650 degrees C. So conventional route of making ODS steel involves prolonged ball milling, canning, degassing, and thermomechanical processing. That's why the ball milling process is very time-consuming, expensive, and sometimes not uniform. And also, it's likely to introduce the contamination during the process. So in this talk, I'm going to talk about the friction consolidation to produce the ODS steel. So the powder will be, let me put on the laser. So the tool, so the powder is loaded here, and the tool moving toward the powder, giving the high compression force while rotating by itself. And the powder used here is produced by the gas atomization reaction synthesis. So later in the presentation, I'm going to refer it to the gas powder. So by combining these two methods, we are going to provide a scalable manufacturing routes for the ODS steels. And also it can achieve higher nano oxide density, and it will deliver structural materials in time for construction of high efficiency, economically viable fusion reactors. So now let's take a look at the gas powder before we consolidate into the solid material. So this is the microstructure from the powder, and this is the EBSD map we took from the loose powder. So the powder has a size of about 100 to 150 nanometer in diameter. And inside the powder, we can see there are multiple grains with a grain size of about 7.7 micron. And on the right-hand side, that is BSC image from with a higher magnification to show the powder surface as well as part of the interior. So we know that in BSC image, higher contrast, brighter contrast usually indicate heavier elements. So by combining this BSC image with the EDS map, so we can clearly see that these bright regions correspond to the yttrium element. And if we take a closer look at the yttrium distribution, we can see that the location of the yttrium can be divided into two places. One is inside the powder. Those exist in the form of yttrium iron intermetallic compound and located at the grain boundaries inside the powder. And another location is the powder surface. The yttrium coexists with the oxygen at the powder surface. This information will be important for us to determine the composition before and after processing. Other than the yttrium distribution, we also wanted to find out the solubility of yttrium, titanium, and oxygen inside the powder. That's why we took one of the sample for APT analysis. Actually, the sample is took from inside the grains. So after we identify all the peaks from the mass spectrum, we can get the composition from those regions. And one important thing is we found the oxygen concentration inside the grain is about 0.1 atomic percent. So this concentration is much higher than equilibrium solubility, which is only 0.01%. And also the titanium concentration in the matrix is about 0.13%. And in this particular region, we didn't see any yttrium. So this is where yttrium should show up, but we didn't see it. So it tells us that either yttrium cannot be dissolved into the steel, or the yttrium concentration in this volume is below the detection limit in the atom probe. And all these numbers will serve as a baseline to understand the effect of friction deformation. So the left-hand side is the picture from the friction consolidated ODS steel. So this puck has a diameter of about 25.4 millimeter, and with a maximum thickness of about 8 millimeter. And the top image is the optical scope from the cross-section view of this puck. So from here, we can see that the bottom, 4 millimeter, especially the bottom corner, those regions are not fully consolidated. But for the top, if we look at the hardness map, we can see that the top 4 millimeter of the puck is fully consolidated, and the highest hardness for this region is about 200, and indicated with the yellow color. And so for the next for the following study, we are going to focus on the on this yellow region, high hardness region. So just to see how grains change, we also did the EBSD map on the high hardness region, and here's the map from here's the map. And then to make a direct comparison, we put the EBSD map from the loose powder at the same magnification. So clearly we can see that the grain size has significantly refined after the friction consolidation. After the process, the grain size reduced from 7.7 micron to about 2.4 micron. So these refined grain size could be one of the main reasons contributing to those high hardness. And we also did the TEM imaging on the same region. So from this field of view, we can clearly see there are multiple precipitates included in the field of view, and the middle 2 precipitates can be clearly identified as yttrium oxide. But for the remaining precipitates, for example, like 3 precipitates here and a multiple here, we can see that there are titanium, yttrium, and oxygen. However, the quantification of those precipitates seems to be quite challenging in the TEM. So here we use atom probe to study the similar region. And in this one particular needle, we were able to catch the precipitates of similar size, which is like several nanometer in diameter. And within this analyzed volume, we only caught like 1 large precipitate. And this image is taken from the same TM lamella, but slightly shifted location. So from here, we can see that there are definitely the precipitates has much smaller size in this region, and also has higher density. So APT happened to, like one of the APT needle also caught a similar region. So we can see that the precipitate had the size of only a few nanometer, and with multiple cuts in the analyzed volume. So to get a composition value, we used the proxygram. So from here, we can see that the peak concentration inside the precipitate is 12% of yttrium, 12% of titanium, and about 16% of oxygen. So considering in atom probe, we usually underestimate the oxygen concentration. So this concentration value actually is very close to one of the phase, which is yttrium 2, titanium 2, and oxygen 7. And also by combining multiple atom probe needle, we were also able to get the number density for those precipitates. So the value we get here is about is 2.3 10 to the power of 22 per cubic meter, and the average size is 4.3 nanometer for those precipitates. As I mentioned that, so after friction consolidation, we do expect some composition change in the matrix. So from here, we can see that the oxygen concentration changed from 0.1% in the loose powder to 0.13% in this consolidated material. So for oxygen concentration change, actually there are 2 competing process. One is that we noticed that there are some oxide shell on the powder surface. So during the friction consolidation, those oxide shell will be break down into small fragments, and those small fragments will be distributed into the matrix, which will increase the oxygen concentration in the matrix. But at the same time, because the oxygen concentration is much higher than equilibrium value, so those oxygen will try to find yttrium and titanium to form those nano oxides. So that will lead to oxygen reduction, oxygen concentration reduction in the matrix. But using our parameter and we found that after consolidation, we do see some slight increase of oxygen in the matrix. And before consolidation, we were not able to detect any of the yttrium, but after consolidation, we do see some yttrium present in the matrix. So for the previous material, previous results I mentioned, those are on the model system for ODS steel. In reality, ODS steel should increase tungsten in the matrix. So once we have the gas powder with tungsten, we wanted to see if previous results can directly apply to the actual ODS steel. So that's why we run a quick analysis using the gas powder with the tungsten. So this is analysis from the loose powder. Again, we try to analyze if there's any titanium, yttrium, and oxygen like dissolved into the matrix. So what we find is that for oxygen, actually this one has quite like a larger amount of oxygen as compared to the previous powder. So we have 0.6% of oxygen in the matrix. And for yttrium, again, we couldn't detect any yttrium in this loose powder at the center. And after consolidation, so from this TEM image, we can clearly see that there are quite a lot of precipitates appear in this field of view. And multiple atom probe needle does caught those precipitates. And the size of those precipitates could vary from like a 10 nanometer-ish or like only a few nanometer. And also the number density are very similar to previous model system. And then when we look at the oxygen concentration, we still see increased amount of oxygen from 0.6% to 0.9%. And before that, we don't see any yttrium. And after that, after consolidation, we do see some yttrium present in the matrix now. So, by looking at this result, we can confidently say that our model system does present the actual ODS steel, like we can directly apply those results. And so to summarize what I just mentioned, so the rapid reaction synthesis with a surgical amount of oxygen addition in the atomization gas stream could lead to the formation of a surface oxide shell, as well as a supersaturated solid solution of oxygen within the solidified powders. And also the friction consolidated gas method demonstrates its unique advantage for dispersing yttrium, titanium, and oxygen species into the powder interior without ball milling. And our initial results reported here have demonstrated the ability to form a high density of nano oxides. So in this study, we were able to achieve 10 to the power of 22 per cubic meter. But for future study, we are going to modify the powder composition and the friction consolidation process parameter to try to achieve even higher nano oxide density. We are looking for like greater than 10 to the power of 23 per cubic meter. At the end, I would like to acknowledge our funding agencies. They include APT&M program and U.S. Department of Energy, Office of Fusion Energy Sciences. Thank you. Any questions?
And thank you very much. Yeah, thank you very much for the good timing and nice work. And we probably have time for like 1 or 2 quick questions. I think there's one question from Qing Chang in the talk. Is that for the so maybe Jia, you can see the talk, you can see the chat for the comparison between oxygen detected and the solubility of oxygen, or the gas contamination evaluated for the tip and or other tips.
Okay, yeah, that's a good question. So we would expect, so we have some baseline, so let me clarify. So the oxygen gas contamination, are you talking about the contamination during the friction consolidation or the contamination during the APT analysis?
APT analysis.
Yeah. Okay, yeah. So for that, we do have the baseline for the oxygen contamination. That concentration is well below the number we measured here. That's why we can confidently say that those oxygen are actually from the material itself. And also, for the APT analysis, if there's any oxidation happen on the tip surface, usually for APT analysis, we don't catch the actual edge of the needle. Usually what we caught is only half of the cross-section area. So I'm not worried about, I'm not too worried about the oxidation on the surface as long as we don't expose the material in the air for too long time.
Okay, yeah, thank you very much, Jia. Thank you.
Okay.
Thank you for all our speakers in this morning. Thank you for all your good timing. I think it's time for our morning break now. And the next session will be start at 10 a.m. Beijing time. So we'll be back after 15 minutes and see you later. Thank you.
In today's challenging environment, scientists and engineers need to accelerate discovery processes. CAMICA offers unique, high-performance analytical instruments to help them unveil the secrets of life and materials at the micro, nano, and even the atomic scale. Founded near Paris in 1929, CAMICA rapidly established its name by pioneering first electron probe microanalysis, followed by secondary ion mass spectrometry, and more recently, atom probe tomography. Ever since, we've maintained our R&D investments at their highest level and partnered with leading academic institutions in order to explore new techniques and technologies. Today, CAMICA is part of the Materials Analysis Division of AMETEK, a global manufacturer of electronic instruments and electromechanical products. We have locations all around the world and strive to expand our reach to new geographical frontiers in order to foster emerging scientific players. Our state-of-the-art production facilities in France and the US allow our experts to develop the most sophisticated microanalytical tools used for research and process control applications in materials, semiconductors, geology, environmental and life sciences. Huge investments are made worldwide towards the development of stronger, lighter and more durable materials for transportation, energy production, aerospace and defense, and consumer products. Materials scientists rely on CAMICA instruments not only to gain a deeper understanding of the properties of materials, but also to predict their performance in real world. CAMICA also accompanies semiconductor manufacturers as they explore the boundaries of physics. Our metrology tools enable the production of latest generation electronic devices, contributing to a world where communication is faster and more reliable. From understanding the microstructures of rocks and the genesis of the solar system to revealing water and soil pollution processes, CAMICA provides the tools for writing the history of the universe and creating a safer environment. Offering novel and powerful instruments for studying intra- and transcellular metabolic pathways, DNA expression, virus penetration, and drug localization, CAMICA enables important medical advancements. Thanks to such a wide spectrum of applications, our instruments have been adopted by top-ranking academic and research institutions, as well as major industrial corporations all over the world. Their satisfaction and success are our main focus. The expertise and passion of our teams will enable us to further push the limits of microanalytical instrumentation and help our customers reach the highest performance in their specialized fields. CAMICA, Science and Metrology Solutions. In today's challenging environment, scientists and engineers need to accelerate discovery processes. CAMICA offers unique, high-performance analytical instruments to help them unveil the secrets of life and materials at the micro, nano, and even the atomic scale. Founded near Paris in 1929, CAMICA rapidly established its name by pioneering first electron probe microanalysis, followed by secondary ion mass spectrometry, and more recently, atom probe tomography. Ever since, we've maintained our R&D investments at their highest level and partnered with leading academic institutions in order to explore new techniques and technologies. Today, CAMICA is part of the Materials Analysis Division of AMETEK, a global manufacturer of electronic instruments and electromechanical products. We have locations all around the world and strive to expand our reach to new geographical frontiers in order to foster emerging scientific players. Our state-of-the-art production facilities in France and the US allow our experts to develop the most sophisticated microanalytical tools used for research and process control applications in materials, semiconductors, geology, environmental and life sciences. Huge investments are made worldwide towards the development of stronger, lighter and more durable materials for transportation, energy production, aerospace and defense, and consumer products. Materials scientists rely on ChemICA instruments not only to gain a deeper understanding of the properties of materials, but also to predict their performance in real world. ChemICA also accompanies semiconductor manufacturers as they explore the boundaries of physics. Our metrology tools enable the production of latest generation electronic devices, contributing to a world where communication is faster and more reliable. From understanding the microstructures of rocks and the genesis of the solar system to revealing water and soil pollution processes, ChemICA provides the tools for writing the history of the universe and creating a safer environment. Offering novel and powerful instruments for studying intra- and transcellular metabolic pathways, DNA expression, virus penetration, and drug localization, ChemICA enables important medical advancements. Thanks to such a wide spectrum of applications, our instruments have been adopted by top-ranking academic and research institutions, as well as major industrial corporations all over the world. Their satisfaction and success are our main focus. The expertise and passion of our teams will enable us to further push the limits of microanalytical instrumentation and help our customers reach the highest performance in their specialized fields. ChemICA, Science and Metrology Solutions.
Okay, everybody, so it's time for our next session in this morning. I hope everybody is back now. So our first speaker is Professor Yuan Wu from University of Science and Technology, Beijing. His topic today, this morning, is the effects of local chemical fluctuations on mechanical properties for high entropy alloys revealed by atom probe tomography. Professor Wu, you can start now.
Okay, can you hear me?
Yes, we can hear you.
Okay, thanks for your introduction. My name is Yuan Wu, coming from University of Science and Technology, Beijing. I'm sorry I changed a little bit of the title of my presentation. The title is Effects of Grain Boundary Segregation on Mechanical Properties of Refractory high-entropy alloys. Firstly, I will briefly introduce high-entropy alloys. Traditional alloy design are usually based on primary elements. For example, for the steels, we usually design steels at the enriched side of the N carbon phase diagram here. So the N and the steel are based on N elements. The aluminum alloy are based on aluminum. Titanium alloy based on titanium. In 2004, a new kind of alloy was reported separately by Professor Junwei Ye and Professor Cantor. This kind of alloy usually have more than 5 or more components with a co-atomic ratio. They are called high-entropy alloys. They are baseless. The first high-entropy alloy reported is N cobalt, nickel, chromium, manganese. They are supposed to have intermetallic phases, but surprisingly, they have only a simple FCC solid solution structure. After that, this kind of alloy was called high-entropy alloy. So, how to remove this? So, the high-entropy alloy is a newborn unique alloy designed by maximization of configurational entropy. When the configurational entropy is larger than 1.61 R, R is a gas constant. We usually call them high-entropy alloy. So in terms of entropy, the alloys can divided into low entropy alloy, medium entropy alloy, high entropy alloy. Although there are some arguments about high entropy alloys, but they do give us some new opportunities for alloy design. For example, this is a ternary phase diagram. For the traditional alloys, we usually design alloy at the corner of the phase diagram. But with the concept of high-entropy alloy, we can go into the middle of the phase diagram. This gives us more opportunities for design of new advanced alloys. And also high-entropy alloy also have some features such as high mixing entropy, severe light distortion, sluggish diffusion, and so on. This make high-entropy alloys great potential for application at extreme environments, such as high temperature applications, low temperature applications, and so on. One example is that when at high temperature, you can have very high phase stability. From this equation, when we have a high entropy at high temperature, the Gibbs free energy will be lower, so they can have the phase can be very stable. For example, this refractory entropy alloys, niobium, moly, tantalum, tungsten, and they are very stable even after annealing at 1,400 degrees C for 19 hours. There is even no green growth. And this kind of refractory high-entropy alloy also has very good high temperature mechanical properties. They can have strength up to 500 megapascal at 1,600 degrees C, and also have very good softening resistance, even comparing with nickel-based superalloy. But they also have challenges. One of the challenges is they have zoom temperature brittleness. From the stress curve, we can see that they have very small plasticity even under compressing. And from the fracture interface, from the fracture surface, we can see that they usually have a intergranular fracture. That means the grain boundary is a weak point of the material, and the crack should initiate from the grain boundary. So what is on the grain boundary and why the grain boundary is weak in this kind of refractory hand alloy. So we use the correlative method of TM and APT. This is a grain boundary here, and this is actual surface of oxiding. From the enlargement and the line profile, we can clearly see that there is obvious segregation of oxiding on the grain boundary. The oxiding may come from the environment or from the fabrication process, and then tend to segregate at the grain boundary, and may lead to the grain boundary brittleness. So what is the form of the oxiding on the grain boundary? We calculate it, we characterize this by the TM, high resolution TM. We can see that no secondary phase were found in this refractory hand alloy with doping up to 5,000 ppm oxiding. They keep the one single BCC solid solution phase, but we see some disordered regions like here, and we find the microcrack initiate from the disordered regions. So we guess this may contribute to the grain boundary brittleness of this refractory hand alloy. So can we remove the amorphous oxide on the grain boundary? So we think about the grain boundary engineering, maybe one choice. So can we replace oxide on grain boundary with some other small sized items such as boron, carbon, and so on? We firstly calculate the segregation tendency. We calculate the segregation energy. This value means the segregation tendency of small sized items towards grain boundary. They can be calculated by this equation. When the value of segregation energy is smaller than 0, that means an item segregating at the grain boundary is energetically favorable. When they are larger than 0, that means an atom segregating at grain boundary is energetically unfavorable. We can find that the value for boron, carbon, and oxygen are all negative. That means all of them tend to segregate at grain boundary, but the value for boron and carbon are more negative than oxygen. That indicates boron and carbon are more inclined to segregate to grain boundary than oxygen. And then we also calculate the strengthening energy. The strengthening energy can evaluate the binding strength of the grain boundaries of the alloy doped with oxygen, boron, or carbon. When the strengthening energy is smaller than 0, that indicates the doping atom will enhance the grain boundary strength. When the value is larger than 0, that means the doping atom will reduce grain boundary cohesion and may cause intergranular fracture. The calculated value for these 3 elements are shown here. Strengthening energy value for boron and carbon is negative, but changed to positive for oxygen doped hand alloys. That means oxygen may reduce the grain boundary strength, but boron and carbon is beneficial for grain boundary strengthening in this hand alloy. Then we do the experiment. We doped boron and carbon into this refractory hand alloys. We found that the BCC structure was kept after doping with boron and carbon. There's no secondary phase were found up to 5,000 ppm of boron and 1,500 ppm carbon. The strength and plasticity was found to be simultaneously increased after doping boron and carbon. The black curve here is the stress curve for base alloy without doping, and these are doped alloys. We can see that the strength and plasticity are obviously increased. And from the fracture surface, we can also see that the doping of boron and carbon changes the fracture model from intergranular to transgranular. And these two figures is the variation of the strength and plasticity with the doping amount. We can see that the plasticity reaches a maximum when doping around 5 thousand ppm boron and 1,000 and 500 ppm carbon. When overdoped, the plasticity will decrease. We can see that when overdoped, there are some boride or carbides formed on the grain boundary of the alloys. This may lead to the decrease of the plasticity. So what is the underlying mechanism of the increased strength and plasticity in the twist of the hand alloy? And we first check the interstitial solid solution inside the grains. We find that the boron concentration inside the grains increase with the total doping amount when the doping amount is lower than 5,000 ppm. And this leads to an increased interstitial solid solution strengthening. This is the reason why the strength was increased. But when overdoped, the formation of boride or carbide on grain boundary consume a high fraction of boron or carbide, lead to the decrease of solid solution strengthening. Then we check what is the origin of the increased plasticity. We also use the correlative method of TM and APT. This is for boron doped hand alloys. This is grain boundary. And from the line profile and the enlargement, we can see that the grain boundary are obviously enriched of boron, but there's no oxidizing segregation were found at grain boundary. So we can see that the boron would preferentially occupy the interstitial sites of the grain boundary and can suppress the oxidizing segregation. And for the carbon doped case, we also find this kind of tendency. The carbon segregates at the grain boundary and no oxidizing segregation at the grain boundary were found. And this is TM image of the grain boundary after boron and carbon and doping. We can see very good connection at the grain boundary, and no disordered regions and microcracks were found near the grain boundaries. So the doping twist boron and carbon change the grain boundary structure and enhance the grain boundary cohesion. Next, we also do the first principle calculation about the electronic interaction to interpret why the grain boundary cohesion was increased. This is a charge density distribution, and this is ERF, electron localization function plot. From this calculation result, we can see that the bond between boron and carbon atom and the host metallic atoms are stronger than that of oxidizing with metallic atoms, and the bond between boron and carbon and metallic atoms are more likely to be metallic bonds, but oxidizing and metallic bonds are more likely to be ionic bonds. So the boron and carbon metallic atom bonds have weaker directivities, directivity but stronger electronic interaction. This may contribute to a stronger cohesion and higher deformability of ground boundaries after doping boron and carbon. So this is my summary. Due to time limits, I will skip this. Thank you for your attention.
Thank you very much, Professor Wu. That's very nice work. And so since we're a little bit behind schedule, so we probably have time for like one quick question. Okay, so if nobody has question at this moment, so probably you can contact Professor Wu later for a more detailed discussion. Okay, thank you very much, Professor Wu. Thank you again.
Thank you.
Thank you. Okay, so our next speaker is from Pangyu Liu from the University of Sydney.
Can you hear me?
Hello. Hi, yeah, we can hear you. Okay.
Thank you, Professor Hu, for your introduction.
Okay, you can start now.
Okay. Hi everyone. My name is Pangyu Liu, and I'm from the University of Sydney. And my supervisors are Professor Julie Kearney, Dr. Isan Chen, and Dr. Patrick Bird from the University of New South Wales. And today I'm going to share about some of our simulation work, like how do we use some conditions we obtained from the experiment to trying to correlate with some of our atom prop works. So first, hydrogen energy can be used for multiple purposes, especially when it comes to decarbonization. Hydrogen fuel plays an essential role in reducing our dependence on fossil fuel energy. And a cost-effective way to transit the hydrogen gas is using the existing natural gas pipes. However, exposing the current peroxide steel gas pipes to hydrogen may lead to the hydrogen embrittlement. So the hydrogen embrittlement is the fact that where gaseous hydrogen is absorbed by steel, which reduces ductility and hence may lead to some early cracking. Therefore, it is crucial to have a comprehensive understanding of this problem. And this is the SEM figure of our Pillai sample. And basically it contains ferrite and lamellar cementite with a large proportion of ferrite and cementite interface. Sorry, due to the matter of time, I kind of put some our experiment result into original observation, and this work is done by our colleagues, Dr. Rami New, and I believe he already have a comprehensive introduction to you guys yesterday. So in our cryo-atom prop experiment, we charge a deuterium inside the specimen to distinguish the hydrogen contaminant from the atmosphere. Here, we can see the deuterium is distributed in both the ferrite and the cementite matrix, while there's a depletion zone existing near the interface in the ferrite. From our quantitative analysis of the carbon concentration, we also observe the existence of hypostoichiometric cementite, which means there are some carbon vacancies inside the cementite. And from our high resolution TM result, we first make sure the interface shows the essential orientation relationship. Also, the interface is shown to be coherent. And we further use the some geometry phase analysis to observe the strength distribution. The color here refer to the strand relative to the pristine ferrite. These two arrows point at the region close to the interface in ferrite and cementite separately. We can see that around the interface, the strand map shows an expansion of ferrite and compression of cementite lattice, which makes us very curious about how these two experiment conditions will affect the interaction of the hydrogen and the ferrite and cementite interface. So here we use the first principle calculation, mainly using density function theory with BUS software, and we also use an algorithm for accounting for a higher carbon vacancy concentration. With the aid of this algorithm, we are able to obtain all the independent configurations in the same concentration of the carbon vacancy. And here are some of our energy used to describe the hydrogen behavior. So we first start from some simple case. Is how the single hydrogen will interact with a single carbon vacancy inside a model, which is the dilute calculation. So here we place the hydrogen atom in the carbon vacancy at different distances. And this figure shows the hydrogen solution energy as a function of the hydrogen vacancy distance. We observe that the carbon vacancy can act as a strong hydrogen trap, while the accretion is actually a short range, with the energy will rapidly converging to that of the dilute hydrogen in a perfect symmetry. And in this section, we want to investigate how the hydrogen will interact with the cementite with higher carbon vacancy concentration. Here we consider 4 different stoichiometrics from 6.25% to 25%. And with the aid of the salt algorithm, where we can obtain the lowest energy configurations for each composition pointed by these blue arrows. And then we place the hydrogen at all interstitial sites in these 4 models. We found that with the carbon vacancy concentration of 6.25% and 12%, actually hydrogen atoms will prefer to stay in the middle of the vacancy. And the presence of the 6.25% vacancies can even lead to a reduction in solution energy of up to 0.1 electron volt. And here we want to introduce the effect by the strand field caused by the lattice misfit. And to better simulate the strand field environment at different positions around the interface, we actually didn't build an entire interface model. Instead, we calculate a series of the lattice parameter values in the interval of pure ferrite and the pure cementite at the happy plane. And these arrows roughly presents the change of the lattice induced by the strand field, and we basically choose the lattice parameter inside linearly inside this region. So we think that in this way we can control the effect of the strand field more accurately. And after we obtain all the lattice parameter, we can therefore calculate the strand matrix, and then we rotate the strand matrix to a conventional coordinate systems that match to our models. And in order to locate the interface position, we also do some elastic constant calculations, and we found out that the cementite will have around 56% of the strand sharing. Sorry, the 56% of strand sharing in ferrite, which means that actually the cementite is a bit stiffer than the ferrite. And in the right figure, the x-axis is the biaxial strand relative to the interface, and the y-axis is the hydrogen solution energy. Here, we calculate a series. We calculate a pure ferrite and a cementite with carbon concentration from 0 to 12.5%. With the strength field vary. And the left side of the points are calculated with the lattice parameter of pure ferrite, while the data points on the right side are the lattice parameters of pure cementite. It shows that in both material, the biaxial compression will actually increase the solution energy while the tension will decrease it. Moreover, the existence of vacancies can further reduce the hydrogen solution energy. So in the previous section, we discussed the energy change versus the strength. Here we applied a one-dimensional strength decay function to obtain the hydrogen solution energy with different distance with the interface to discuss the hydrogen solution energy versus the location. So hydrogen atom at that in ferrite will get attracted to the interface because of the tensile strength, as the tensile strength will decrease the hydrogen solution energy as shown in the figure. When the hydrogen reaches the interface, the existence of the big jumping energy that the hydrogen will go into the cementite. And this is exactly what we've seen in our atom prop observation. So practically, our DFT calculation is in agreement with the result we have seen from the atom prop. And the carbon vacancy in cementite will form a strong hydrogen trapping sites, which can be up to 0.3 electron volt. And a hydrogen in depletion zone will drain to the cementite matrix due to these trapping sites. And here are my summary. And also due to a matter of time, I'll stop here and welcome any questions. Thank you.
Okay, thank you very much. Thank you very much, Pengyu. Thank you for very nice work. And and also thank you for the good timing. And we probably have time for like 1 or 2 questions. Oh, so from Dr. Takahashi.
I'm sorry, where is the question?
I think we have to ask the admin to release the silence of Dr. Takahashi.
Okay. Hello?
Okay,
Hello?
yeah.
Okay.
Oh, okay,
And maybe you know the cementite is so stable phase in carbon ion system. And why, my question is why cementite has a carbon vacancy? And it well known the cementite composition is 25 atomic %.
Okay. It is actually because some of our quantitative analysis toward the carbon vacancy in a cementite phase. And we all know that actually the carbon concentration is very hard to underpin in an atom prop. But we actually, especially in a 24 data peak, because there's a lot of overlap over there. So we kind of overestimate the carbon concentration by assign the 24 data peak to C4. And however, the maximum carbon concentration we measure in cementite is still 22%, which means that there must be some carbon vacancy inside the cementite. Okay. Also from some of
Yeah. This is atom probe result. Okay.
Yes.
And it concludes it contains some so mass assignment program. And my question is in metallurgy, why the cementite is very stable phase in carbon ion system. Why the cementite has a carbon vacancy? It means a low carbon composition than the 25 atomic %. It's a no deformation. Okay, it's the cementite after heat treatment. So I guess it's so stable for cementite.
Yes. So maybe it might experience of some cold drawn process, so they may cause some deformation around the cementite. So yeah, it's probably that it's because of some of the cold drawing process, I think.
Okay. Okay. Thank you, Dr. Takahashi, and thank you very much, Pengyu. And I think we can move to our next speaker, Dr. Hui Li from Shanghai University. His topic today is the precipitation of secondary phase in Inconel 617 alloy during aging process. Okay, Dr. Li, you can start now.
Can you hear me?
Sorry, I think it's something wrong with your voice. It's kind of, the volume is not large enough.
Hello?
Yeah, we can hear you now. Okay.
Hello, everyone. I'm Hui Li from Shanghai University. My topic is the precipitation of the second phase in Inconel 617 alloy during aging process. First, I would like to introduce about the alloy. It has a high temperature strength and high resistance of oxidation and corrosion. It's a nickel-based super alloy, and it's an important structural material for power plants, including some coal-fired power plants or nuclear power plants. The strength and corrosion resistance is the main property of this alloy, and the microstructure influence the strength of this alloy. Many papers have shown that the microstructure of this alloy is there are some carbide in matrix and at green boundary, and some gum prime phase in the matrix, which give the strength improvement of the sample. And after longer aging time, the strength will decrease with the aging time. Some TM microscopy and some calculation about the two phase have given by many researchers. So it can conclude that the size and the density of the gum prime particle and the carbide can give can influence the property of the book samples. And some papers show that the green boundary segregation of carbon, boron, and chromium, and molybdenum, and some interface segregation of gum prime and carbide interface. So there are some questions we can derive that the aging hardening process introduced by the secondary phase should be further studied. Another co-precipitation of behavior of the two type of secondary phase is still not clear now. So we have carried some experimental to review the co-precipitation process of the two type of the secondary phase. The composition of the alloy is nickel-based super alloy. It contains some chromium and iron and so on. First, we solution annealed the sample and water quench to get homogeneous state of the sample, and then we aged it at 700 centigrade for until 1000 hour to create the secondary phase precipitation. And then we use atom probe, TM and SEM to analyze the microstructural features of the different sample. After the hardness test and SEM observation, we can see that after aging at 700 centigrade until 100 until 1000 hours, the hardness increased until 160 hours, and then the hardness decreased slowly during the aging time prolonging, which is introduced by the gamma prime particle homogeneous distribute at the matrix. We can see that during the early stage of the aging, some plate-like carbide precipitate at the matrix, and some irregular shape carbide precipitate at the green boundary. Few of the gamma prime particle can be observed by the ICM image in this sample. After aging for 40 hours, some gamma prime particle can be observed near the carbide plate. And during the aging process prolonging, we can see more and more gamma prime co-precipitate with the carbide in the matrix. And after the longer aging time, most of the carbide disappeared in the matrix. They only precipitate at the green boundary, and the gamma prime homogeneously distribute in the matrix is the main features of the sample after aging for more than 300 hours. After then, we have measured the size and volume fraction of gamma prime and carbide using more than 10 SEM image for each sample, and we can see the trend of the different sample or different secondary phase. The size of the gamma prime increased with the aging time prolonging. However, the volume fraction reached to the peak value at aging for 160 hours, and then the volume fraction of the gamma prime decreased slowly during the aging time. As can see that this time is the peak hardness, so the gamma prime should be the best strengthening phase in this alloy. And we carried the TM observation of the different sample. We also can see the co-precipitation of the secondary phase, and the feature is similar to the ICM image. We have carried some HRT observation. We can see that the gamma prime precipitate near nucleate near the carbide with the irregular shape. After longer aging time, the gamma prime is nearly spherical. All the second phase are coherent with the matrix and coherent with each other in the same greens. The SPM analysis shows that there are chromium enriched at the carbide and diplet at the gamma prime, and nickel and aluminum enriched in the gamma prime and diplet at the carbide, but we don't have the quantity composition analysis at the STM date. So we use atom probe to analyze the composition of the different secondary phase and different interface during the agent process. We have observed that there are some separate precipitate carbide and gum frame and co-precipitate carbide and gum frame, and we will analyze them separate. We have enlarged the sample and cut a small box which containing carbide or separate gum plate or gum frame and carbide co-precipitation to observe the partition of different elements. We can see more clearly about the element partition behavior. And then we have measured the combination across different phases. We can see that the aluminum and titanium segregate at the matrix and the carbide interface, which can be act as the nucleation site of the gum prime particle, because most of titanium and aluminum will enrich in the gum prime particle, and some other elements have segregate at the gum prime carbide interface. And we don't observe any segregation at the gum prime and matrix interface. And we have measured the partition ratios of different elements. We can conclude that if there are another secondary phase near one secondary phase, the partition ratio of the element will a little lower than that of the separate precipitate secondary phase. And we can see that features of structure interface, because we can see that from the HRTM, we don't see any transition phase or some transition regions at the interface, but we can see that the width of the compositional interface is decreased with aging time. So they are contradictory. So we can conclude that the precipitation process is controlled by the diffusion process. And then we can conclude that the precipitation process of the different secondary phase. The carbide nucleate at the matrix first and impale the aluminum and titanium and nickel, and then the gum prime nucleate around the carbide, and they can act as a stepsicle for the carbon and chromium diffusion to the carbide. So carbide will destroyed in the matrix and only precipitate at the green boundary, and the gum prime particle homogeneously distribute in the matrix. So we use atom probe PM and ICM observe the microstructure of a nickel-based superalloy and conclude the precipitation process of different second phase. Thank you very much.
Thank you very much, Dr. Lee. It's a very nice timing and great work. And I think we can have one quick question. Okay, so if there's no question, then probably anybody has the question can contact Dr. Lee later after the meeting. Yeah, thank you very much, Dr. Lee.
Thank you.
Okay, so probably we can move to our next speaker, Siyu Huang from University of Sydney. Hello, Siyu, and the topic for Siyu today is the nanoscale distribution for alloy elements in optimized zero using the Inviso 6000. Okay, you can start now. Sorry, so we can't hear you. I think you're still silenced. So please remove the silence of your microphone.
Okay, I need
Okay.
to, yeah. For that.
Yeah, we can hear you now, but your voice is a little bit small, so.
Can you hear me now?
Yeah. It's
Okay,
great now.
Okay, thank you for your introduction. So I start. Hello everyone, I'm Xu Huang. I'm a PhD student from the University of Sydney, supervised by Professor Julie. Today I will give a presentation on nanoscale distribution of alloying elements in optimized zero using the Inviso 6000. As we know, the cooling alloys are commonly used as fuel cladding in pressurized and boiling water nuclear reactors due to their relative transparency to neutrons and their good mechanical and cooling properties. This project is focusing on the non-irradiated optimized zero. We received optimized zero tube from the Westinghouse as figure 2 shown, and the table shows the composition of optimized zero. First, I will talk about the sample preparation for both APT and TM experiment. I use the double electroporation method to rough pollution at 12 volts and fine pollution at 5 to 7 volts. I try to directly run the electroporation sample in lab, and it's with a really low success rate. However, with the field process, it can run smoothly. So I tried site-specific anonymity on electroporation sample to locate the more interested area. Luckily, the only electroporation sample can run smoothly by Inviso. All the APT data were analyzed by AP06 software. Some TM samples were prepared using the conventional default procedures and run TM experiment on seamlessly. All the TM data were analyzed by Velox. Before I show my data, I would like to introduce the Inviso 6000 instrument, which some experiments in this presentation were carried out by Inviso 6000. Recently, Kamika Inviso 6000 is introduced to our microscopy center. The breakthrough techniques have totally changed the cooling sample studies. The first picture shows the working principle of the conventional local electron atom bomb. As all of us are quite familiar with it, I won't explain it. The Inviso 6000 3D atom bomb microscopy introduced major techniques breakthrough to push the boundary of the atom bomb analysis. We put a single needle into the counter electron, then using dual laser to hit the sample. After the ion evaporated from the surface, it was accelerated by a match, then fly to the director, which can reach a broader field of view. Its ultra-wide field of view, flight path, and unique dual beam deep UV laser persistence result in a higher single sample yield and a greater analyzed value with improved reconstruction fidelity, allowing more information to be obtained from each dataset. For more details, you can about the Inviso 6000, you can refer to the white talk yesterday. The cooling alloys are historically difficult to run in atom bomb, especially only with electroporation sample preparation. It has a really low success rate. Currently, in nearly all the cooling atom bomb study, the sample preparation for the tip involves the field process. However, it's widely known the conventional field process will produce artifact hydride, which is bad for the experiment, especially studying the hydrogen in the material. Cryofib can solve this problem. However, it's quite more time-consuming and complex. Without field preparation, the tip will have an oxide layer out of the cooling matrix. In the leaf system, the laser pulse will hit one side of the tip, which will cause a non-uniform evaporation, and the voltage will keep increasing to reach the site detection rate goal. When the voltage reaches quite a high value, the other part of the oxide starts to evaporate. Once the matrix under the oxide, the high voltage will cause the tip to fracture directly. In the TM result, it's quite clear to see the different phase in the cooling matrix. The EDIs were carried out to quickly identify the beta niobium and the cooling niobium ion lava phase due to different composition. Here, the right bottom two precipitate are contain both iron and niobium. So there are iron niobium, the cooling niobium ion lava phase. All the beta niobium are in round shape. Looking at the yielding point, there is a significant increase in typical yield for different alloys in Inviso 6000. Tips usually run smoothly and rarely fractures. Samples usually can hit the voltage limit or ion limit. Yesterday, my colleague Dr. Liu showed the experiment of aluminum in vessel. The yielding improvement is noticeable, but it's not an important improvement. However, yielding improvement for the kaolin alloy is profound compared with aluminum. To be noticed, all these samples were prepared only by electropolishing. The maximum data got by LEAP 4000 is only 13 million. All the other samples are fractured quite quickly, usually less than several minutes or even less. In addition, the longest one is hard to repeatable in the same way sample preparation. I will explain the reason in the later slides. However, all the random electropolishing sample runs mostly in INVISO 6000. Every tip can run more than 100 million data. Some tips can get more than 500 million data, which provide us to get micron-size reconstruction data. And this experiment with lower yield is carried on at 400 picojoule. All the other points are carried on at 800 picojoule. Here is the parameter used in LEAP 4000 and INVISO 6000. In our center, we try many experiments for compare different samples. So compare the different laser energy and evaporation mass spectrum in both instruments. INVISO has nearly 4 times field of view compared to LEAP 4000. So the detection rate too in the INVISO is similar with 0.5 detection rate in LEAP 4000. And the 800 picojoule laser energy in INVISO is similar with 100 picojoule in LEAP 4000. Let's look at the two figures obtained by LEAP and INVISO. As the figure shows, the INVISO 6000 data has a great field of view. It also provides an opportunity to study the oxide layer of the kaolin. And the LEAP data is the best data as shown in the yielding figure. And the beta niobium is exactly located on the top of the tip. As I mentioned before, which is hard to repeatable because the precipitate is exactly located on the top of the tip, which benefits to form less oxide. So it survived longer. As we know, for the kaolin alloys, the pole in the LEAP is not clear. So usually we cannot use the pole to reconstruct the kaolin data. However, the pole is quite clear in the INVISO data, and the large field of view contributes to providing more poles, which result in a crystallographic-based reconstruction. This is the data I shown in the last slides. With zoom in the region of the interest, we can see the iron is decorated at the interface between the beta niobium and the alpha the kaolin by the epoxy function. As the right figure shown, we can find that iron is quite clear in the interface. In order to figure out the real thickness and how iron decorates at the interface, the EDS and STEM were carried out at the interface between the beta niobium and the alpha the kaolin. Figure A is the half of the interface. The bright items are beta niobium, and between the interface, the gray items are iron. It's clear that beta niobium precipitates were seen to be coated in a continuous near multi-layer of iron. These two figures show the different elements iron fractions change from the beta niobium to alpha the kaolin. Let's see the other data. This tip is flipped after electropolishing, and in this data set, this tip is with a green boundary and a small beta niobium at the left side. There also has the kaolin niobium iron lava phase at the bottom of the tip. Due to the yield and density, in order to capture the lava phase, has to run the site-specific sample preparation. Unfortunately, this tip hadn't acquired long lava phase data and fractured. Let's look at the mass spectrum. The mean peaks in the INVISO are kept same with the LEAP 4000, but the INVISO 6000 show more peaks compared with LEAP 4000 due to complex ion evaporation. Let's look at the data from INVISO. You could get a fantastic long APT data, like the video shown, we got more than 1 micron data. And with the pole reconstruction, the beta niobium shape is round and quite kept same as we saw in under TEM. And in this tip, 2 complete beta niobium is observed, like the deep data. They also have iron decorates at the interface. One interesting point is 1 and 2 Dalton are also rich in the first beta niobium, but this tip is long charged sample, and hydrogen may come from during the electropolishing from the analyzed chamber. In future work, I will charge tutorial to optimize zero to distinguish hydrogen to see the result. To be noticed during the chemical charging, an oxide layer will form on the tip, so it's resulted in a low yield, even carry on in the cryo vacuum transport system in LEAP 4000. However, because InViso has a good ability to run the sample without with oxide, InViso can improve the hydrogen exploration experiment success rate. This is a video ion and niobium clapping from the front to the back. You can tell the ion layer is continuous covered by beta niobium. The second video is only with ion, which is more clear. Beta niobium isosurface is created to measure the element change around the beta niobium. Ion, niobium, and the zirconium change is similar to the LEAP data, and 1 and 2 Dalton are also increased when it comes into the beta niobium. Here is the second beta niobium, the smaller one. The second video shows the ion and the niobium clapping from the front to the back, which can tell the ion layer is also continuously covered by the beta niobium. The third video only include the ion. From the ion concentration, we can know the second beta niobium trapped less hydrogen compared to the first one. Here is another data set obtained by InViso. A long green boundary more than 400 nanometer is observed, which enrich ion, which also keeps same with the LEAP data. Here, we also observe the dislocation from the low green boundary. The zirconium niobium ion lava phase is also observed by InViso in the right electropollution sample. The right video is the ROI region in the first video. The composition analysis result is shown in the table. InViso 6000 can have improved yield and has a great field of view, which makes the APT experiment for the zirconium alloys easier. And in this work, we identify the ion segregation both around beta niobium and green boundaries. In the future, I will try the chemical charging sample in the InViso to figure out whether these features can contribute to trapping the hydrogen or not, and investigate the APT analysis of hydrogen in the different zirconium alloys, which is a potential reference material for future zirconium mass spectral interpretation. Here, we need to acknowledge the University of Sydney, University of New South Wales, Midas, Microsphere Australia, the University of Manchester, Westinghouse, and also need to thank the Michael, Andrew, Technology, Vijay, and Asa. Here is my email address and contact details. If you have any more questions, you can feel free to contact me. Thank you for your attention.
Thank you very much, Ziyu. Thank you. So is there any questions? We probably can take one question. Okay, I think I have one question for you, Ziyu. So we noticed that during the InViso 6000 analysis, the laser energy is much higher than normally we use in the laser energy range for LEAP 4000 or LEAP 5000. Is it related with the different laser?
Yeah, because in the InViso is the laser the laser mode is totally different with the traditional LEAP 4000 and LEAP 5000. The laser is come from they have two lasers. One is upper laser and the lower laser from two sides. For the laser energy, we simulate the 100 picojoule in the LEAP 4000 is similar with 800 picojoule in InViso. Similar, yeah, but not exactly the same. For more details in the for DY and Andrew explained that point in yesterday's presentation. Yeah.
Okay. Yeah. Thank you very much. Thank you.
Thank you.
Okay. Okay. Thank you, Ziyu, again. And now I think we can move to our next speaker. Guangyan Sun from Shanghai University. Hello, Guangyan.
Hello.
Hi, hello, Guangyan. Hi. So Guangyan's topic today is a study on precipitates phase in custom 455 margins stainless steel. Okay, I think you can start now, Guangyan.
Okay. Hello, everyone.
Guangyan, is this your first slide or? Is this your first slide?
Can you hear me?
Oh, we can hear you, but I didn't see your title slide, so I don't know if this is your first slide. But if so, you can. Oh, okay, yeah.
Okay.
Yeah, okay. You can start now. Yeah.
Okay. Hello, everyone. It is a great honor to participate in this conference in Nanjing. My name is Guangyan Sun, and the title of the report is the study of the precipitation phase in customer 455 stainless steel. 455 stainless steel is developed on the basis of the first generation of magnetic precipitation hardened stainless steel, stainless W. Compared with other stainless steels, 455 stainless steel has both copper and titanium added. Whether the copper, nickel, and titanium elements contained in 455 stainless steel are related to high tensile strength is the focus of our research. For example, 11 for precipitation hardened stainless steel use copper to form a copper-rich phase during the tempering process for precipitation strengthening. 455 stainless steel heat treatment process is simple, and because of its high strength and toughness, excellent resistance to environmental corrosion and other capabilities, it is widely used in aerospace and modern fields. Its wide application is attributed to its high strength and toughness, and we believe that the precipitation of copper, nickel, and titanium atoms during tempering is the main reason for the high strength and toughness of 455 stainless steel. The heat treatment process of 455 stainless steel is simple, and high strength and toughness can be obtained by single step etching treatment after solution treatment. In the tempering process, the second phase will be precipitated, and the boron mechanism and sealing mechanism will be used to strengthen so as to obtain high strength. At present, there is not much research on 455 stainless steel at home and abroad. All the research is not in depth. Nielsen et al. Studied the mechanical properties of 455 stainless steel during tempering as early as 1994. The authors argue the increase in hardness during tempering is attributable to the precipitation of the nickel-3 titanium phase, and the subsequent decrease in hardness lies in the roughing of the precipitation phase. The author only gives the hardness change curve, lack of characterization. The existence of copper will cause copper-rich phase precipitation, and whether the nickel-3 titanium phase is really precipitated is still a question. We focus our later research on the characterization of the precipitated phase. Anderson et al. Took a step forward in the study of the precipitation phase of 455 stainless steel, characterizing the atomic distribution during the tempering process of 455 stainless steel. After tempering for 25 minutes, spherical clusters with nickel and titanium atomic content close to 421 were found, which were thought to be precursors of the nickel-3 titanium precipitation phase. After tempering for 2 hours, the nickel and titanium atom content was close to 3 to 1, and it was believed the nickel-3 titanium was formed at this time. The author believes that in addition to the nickel-3 titanium precipitation phase, there is also the existence of copper-rich phase, but the precipitation of copper in the figure is not obvious. The question we will study is whether the copper-rich phase and the nickel-3 titanium phase precipitate, and what's the precipitating relationship between the two types of precipitated phases. We tempered 455 stainless steel at 480 degrees Celsius for 4 hours and characterized the copper-rich phase and nickel-3 titanium precipitated phase by TEM and APT. Bright field images are difficult to distinguish the second phase precipitate, and the selection election diffraction image can be seen with 3 sets of spots, namely the magnetic matrix, the nickel-3 titanium phase, and the copper-rich phase, at which time the copper-rich phase is a face-centered cubic structure. Through the dark field image, it can be seen the spherical copper-rich phase and the load-like nickel-3 titanium phase are dispersed in the matrix. And the positional relationship is as follows. The large size copper-rich phase is a face-centered cubic structure. The reason for the large size is that it's not coherent with the matrix, and the closed packed surface of nickel-3 titanium provides a gross position. Atomic distribution mass can be seen that copper, nickel, titanium, silicon, and nanobium atoms have significantly polymerized, forming clusters or precipitated phases. Nickel and titanium atoms gather in the same position to form a nickel-rich phase, which precipitates adjacent to copper atoms. The copper-rich phase is surrounded by load-like and spherical nickel-rich phase. Make isotope concentration surfaces of each atom separately. The copper-rich phase varies in size and size, and the quantity density is high. The large size copper-rich phase is a face-centered cubic structure, and the larger size may be related to the precipitation of the load-like nickel-rich phase. There are 2 types of nickel-rich precipitation phases, adjacent to the copper-rich phase. One is load-shaped, larger in size, and the ratio of nickel and titanium atomic content is close to 3 to 1, which is the nickel 3 titanium phase. The load-like nickel precipitated phase contains a high content of nickel and titanium, but a very low content of silicon. One type is spherical, small in size, and the proportion of nickel, silicon, and titanium atom content is close to 16 to 7 to 6, and it is speculated that it may be J-phase. The spherical nickel-rich precipitated phase contains a high content of nickel and titanium, and the content of silicon is higher than that of titanium. The conclusions of the study are as follows. The most important conclusion of my research is that the presence of copper-rich and nickel-3 titanium phases have been demonstrated. There are two. The current research focuses on the use of characterization to determine the precipitation of copper-rich phase and nickel-3 titanium phase. There are two types of nickel-rich precipitation phases adjacent to copper-rich phase. One is load-shift, larger in size. It is speculated that it may be nickel-3 titanium phase. The copper-rich phase is a face-centered cubic structure. One type is spherical, small in size. It is speculated it may be J-phase. The copper-rich phase is a body-centered cubic structure. Follow-up research, I will use different time periods for temporary. The precipitation relationship between the copper-rich phase and the nickel-3 titanium phase under different temporary times to characterize. Thank you for listening. Okay.
Okay, thank you very much. Thank you, Guangyan. Is there any questions? I think we can have one question, one quick question.
I'm present.
Okay. So if there's no question, then I think we can move to our next speaker. Thank you very much, Guangyan. Thank you again. If anybody interested in this work, you can contact Guangyan later for more detailed discussion. Okay, thank you.
Thank you.
Thank you. Okay, so we are right on time. So now it's time for our last presentation in this morning. It's from Jamaica, Dr. Robert Ufik. So it's our old friend, right? And okay, I'll leave it to you, Rob. So you can start now.
All right, great. Can you see my title slide and hear me well?
I think Guangyan should stop sharing. Okay, and Rob, you can start sharing your slides.
Okay, looks like I'll have to quickly start again.
Okay, yeah, we can see you.
You can see the title slide now?
Yeah, we can see your title slides now.
All right, great.
Okay, great.
All right, well, yes, thanks for sticking around to the last talk before the lunch break. And thanks to all the great talks already, and thank you to the organizers for giving me a few minutes to spell out the specific goals, features, and the benefits brought to the Atom Pro community by our new 6000 product line. So here we are looking forward by looking backwards. Sometimes we think innovation comes way too slowly, and I feel the same way about all sorts of things. But to counter that, it's worthwhile to consider how far we've come
atom probe tomography can be challenging microscopy to pursue, but it really enables gathering unique information, right? That treasure chest of data that can't be captured any other way. And it's become so much easier. So the vision of Tom Kelly in the late 1990s of turning a slow and difficult technology into a microscope that can be used by the masses was already achieved in 2003 when we shipped our first system to Oak Ridge National Laboratory. And we've come a long way since then. And as it says below the picture on the right, this atom probe, our first system is now at John Panix's museum. You can see the website there if you'd like to check it out and go visit him in person if you'd like, I'm sure. So moving forward 20 years, we've grown user base from a few dozen people using about 10 instruments scattered at a few sites around the world to about 140 atom probe systems operating in something like 17 countries. Literally thousands of people using atom probe tomography in their work to improve the understanding of materials. And we're very excited about this. The advances during this time would take hours to cover, but clearly we have moved the technique from a niche. Okay, we haven't moved it to mainstream, but we've moved it to a very popular niche technique with a broad base of applications and improved the time to knowledge by literally orders of magnitude, such that even semiconductor companies are using this technique to monitor inline processes. So that's a testament to a microscope reaching its mainstream applications. So we'll briefly introduce the 6000 product line, talk about the design targets, the system's features, and the benefits that those features bring. Sorry about that. And I'll show you some of the great data, but to save, I'll show you some great data, but to save all your time, I suggest you see the presentations from the other great work from the University of Sydney, our partner in crime for the development of this Visa 6000 microscope. They've really shown some great examples of both improved yield and data quality with amazing fields of view while still maintaining that high mass solving power and single tails. So first, we'll cover the LEAP 6000 XR system. So this is a reflectron-based system. Going back several years ago, we started formulating what the goals of the next products would be. In this case, we knew the community, including the semiconductor manufacturers, wanted a high-performance system that required fewer expert users to create high-quality data and be able to do this in a shorter period of time. So these are some of the design criteria that we put together. We knew it would be a microchip compatible system and would have to include substantial improvements in automation above what was available in the early 5000 systems. So at least one version of this product line would indeed be a reflectron design, and that's what the 6000 XR is. And all of our experiments to date show improvements in data quality with decreasing wavelength of the laser. So we knew it would include a deep UV laser system and all the challenges that brings with trying to bring in deep UV light through an optical system and focused to a focused spot inside an ultra-high vacuum system. And we also theorized that a hybrid pulsing system, meaning a combination of voltage plus laser simultaneously, would improve signal to noise in at least some material systems. And that's the theory at the time, and you can build it before you can discover that. So starting out with increased yield, for example, as we've done for well over a decade, we go to our favorite specimen in what we call the yield sample at Pika. This is a doped polysilicon, 100 nanometers, 112 nanometers of oxide on crystalline silicon. And this sample has just the right characteristics that if you use the wrong run conditions, you get both poor data quality, meaning bad spatial and spectral resolution, and poor yield. And we've used this type of sample to optimize both software and hardware for many years. And it has not disappointed us during the development of the 6000 products either. We found, moving from a reasonable conditions in a 5000 UV laser system, where we could achieve 20% success rates in analyzing through this interface. There's a weak interface at that oxide layer. But introducing a fourth harmonic 257.5 nanometer wavelength deep UV system, we could get substantially better success rates with yield, going up to even 90% success rate. Not only could we get high quality data at higher success rates, but we could collect the data at over 5 times the previous detection rate. So with a quadrupled yield and a 5 times faster data collection rate, our time to knowledge for a sample like this, and for some material types like it, is increased by a factor of 20. So sure, there's some groups where speed is not absolutely required, but there are teams around the world where time is literally money. And this kind of performance, combined with the automation where the system can run as many as 25 tips completely unmonitored, means huge benefits. And so the system does things like automatically test electrodes when there's a fracture event, move and focus the laser onto the next tip, and just move on through chain acquisition. So it's some really exciting stuff that allows faster time to knowledge and frees up users to do other more important actions than sitting at the tool and monitoring what it's doing. So we've shared some of this data before, but in addition to the improved yield reported by the Sydney group, we have others examples of this. This yield benefit is not a unicorn. There are many examples of it, and I'd like to share this other example. This project is centered around a family of materials that often has poor yield and data quality, so perovskites. At Kamika and Madison, we've run several different versions of these materials, and sometimes you can get acceptable yield and data quality, but the majority of the time, these materials are weak and they rip themselves apart prior to collecting useful data. With the introduction of the 6000 product line, Dr. Jonathan Popowski requested we try to analyze a set of materials that he was unable to get useful information using his UV laser system. So the first thing to note is the huge increase in run size from the DQV LEAP 6000, the data that we see here in the red box. And so those are 12 and 16 million ion runs, where those data sets were turned off after collecting the entire region of interest. So not only were the volumes collected orders of magnitude larger, but it was done with just a few specimens prepared, and the spectral and spatial quality were excellent. So this is another clear example of the improvement in success rates with the new laser system with some applications. Obviously, we haven't tested everything out there, but we've been very pleased with the results in many applications that we've worked with. Here's a mass spectrum from perovskites. And so we can see here this excellent spectral quality from the DPV system. And yes, these are log scale charts, something that we atom probers take for granted. The inherent signal to noise of atom probe tomography has been excellent for a very long time, but can get even better with improved laser systems and reflectron-based systems. So when analyzing these specimens in UV pulsing, the data quality and mass resolving power was substantially worse. And here we can see that the mass resolving power is high enough that although we can't really resolve in that center green peak there, can't really resolve the oxygen and titanium peaks independently, we can at least recognize that there's clearly a peak overlap and 2 peaks residing in that. And so we can really pull out some great depth profiles and actually measure lattice spacings in these materials. So some really great demonstrations of the benefit of the efforts that we went through to work in the 4.5 laser system. So the last note that I have on the LEAP 6000 XR system is the introduction of the hybrid pulsing. So our theory was that this pulsing would improve signal to noise, and it has been coming true, and we're very excited about it. We've not had a lot of time to experiment with it, and there's many applications that we'd like to attack, but we have shown that if we go from just a simple laser pulse to a hybrid mode where we have voltage and laser pulse at the same time, we can show some dramatic improvements in data quality. And so you can see here, this is of course just a simple pre-sharpened microtip silicon line, but we've also had preliminary data on other materials showing improvements in signal to noise from a factor of 2 to a factor of 15. And so this is not one-off or cherry-picked data. This is stuff that we see on a regular basis on at least a variety of materials. We do really look forward to seeing and showing more soon, especially in conjunction with some of our early adopters of the system. We should have 2 of these systems installed in the field very, very soon, and we'll be able to then, of course, work through a lot more different applications. So now we'll shift gears to our wide field of view INVISO system. We've already seen some great results from our partners in Sydney, and we look forward to seeing more soon. We're really excited about that. So the INVISO 6000 design goal was to provide a high-performance, wide field of view instrument with excellent data yield. The instrument was, the design criteria was to allow the collection of large volumes of data rapidly and open up applications with this wide field of view and the larger volumes, being able to do things like more easily compare TEM images with atom probe images. And so this has been achieved by developing the dual laser DPV optical system and its patented electrostatic design that can deliver simultaneous and symmetric laser pulses to the specimen. So being able to improve the reconstruction fidelity by having a symmetric illumination from each side instead of just a single side, like all atom probe systems like the state. So during these design criteria, it's kind of a give and take. We would go to the engineering team and say we would like the world, and they would tell us that we couldn't have the world. And it's really pretty impressive that we're able to provide this wide field of view without giving a trade-off in mass resulting power. Typically, when you're doing these types of electrostatic flight path designs, you gain things in full with half max, but you're going to give things up in, say, pulse rates or in field of view. And in this case, you can see here, the left would be the edge of the detector, where on the right side is the center of the detector. We plotted here the 5000 XS system, the mass resulting power full with half max, and the Inviso, which we had achieved on a regular basis, exceeded the mass resulting power of the 5000, not just in the central region of the detector, but all the way up to the edge simultaneously. So this is some really spectacular data that we put together. And so this is this novel electrostatic design, which we've seen a couple of different cartoonish pictures of it before. Here's my version of it. We have our 5000 system with ions going through the local electrode. And some of those ions either hit the local electrode or hit the vacuum walls instead of impacting the detector. And now by adding in a thin mesh close to the specimen and having a flat counter electrode, we're able to direct those ions onto our 80% open area microchannel plates and be able to collect as much data as possible from the tip. Depending on the shank angle and the tip radius, you can actually capture the full volume, the full field of view of some samples. Not every sample. The shank angle does actually affect some of the image compression factor at the edge, but with the right shaping, you can actually capture the entire field of view. And here's an example of that. This is a LED device. You can see the purple is Indian quantum wells that set the color of the laser light. The light blue is a lunar enrichment layer called an electron locking layer. You can see in a LEAP 5000 field of view, we wouldn't really capture and understand what was going on with this device. This is showing a crystalline growth defect called a V defect that is has a very high density during the growth of these materials, and it, of course, shorts out the quantum wells and makes the LED not function properly. And so by being able to have this ultra wide field of view where you can see the oxidized edges at the edge of the specimen, by having this full field of view, you can really understand the feature better. In addition, this makes specimen preparation easier, because when you're doing those final sharpening steps in the focus dye beam, it's quite easy to be off by 10 or 20 or 30 nanometers and perhaps miss your region of interest because it's on the edge of the specimen and not the center. Well, here you'll have a higher probability of being able to capture all that data at the same time. So some really exciting stuff that we do and see with a wide field of view. And as I mentioned before, thank you, Dr. Green and Peg, and the other Sydney people I presented just a couple of presentations ago. I wasn't able to capture their slides quite yet, but here we've seen a wide variety of the field of view, the data quality, the mass spectral quality, the improved yield that the DPV laser has come. The University of Sydney is a beta site for the Inviso system. They've shown not only the spectacular data, but they've also shown things that they have questions about, things about reconstruction towards the edge of the data set. And this is exactly why we have such a great data partner in Sydney. They're obviously one of the premier atom probe groups from around the world, and they're able to quickly give us feedback on things that they really like about the system and things that need to be changed. So we really do appreciate it. Some of the last things that I'll talk about here before we can head off to lunch is something about why do we get this improved yield? At least in this yield specimen, we can see some things that really give us some indication of what's going on. This chart shows the voltage profile for the number of ions in the x-axis, basically depth into the sample, versus the voltage, this kind of VZ curve that you see in atom probe data. And this gives an indication of the required field because field evaporations. So this experiment was completed on that yield specimen that I previously discussed. And the buried silicon oxide layer generally requires a higher field to evaporate when running in the UV system like the LEAP 5000 or LEAP 4000 system. And so you can see a typical voltage plot in that the blue dotted line from those UV systems. And then you can compare that to the smooth evaporation. The thin red line is from a homogeneous silicon specimen. And it's obvious, you can see that the deviation of the blue dotted line and this extra voltage will result in an extra physical stress in the specimen. And this is what leads to specimen failure. Fracture at that point, and then you don't collect data from the region of interest, especially on materials like this that might have weak interfaces. So, about that. In addition to this reduction in field, which we believe is because the oxide and the silicon are absorbing the DPV laser light more uniformly, resulting in a more uniform field as we go through this layer. The wide field of view also allows the detection system to see when those layers are coming in. So if you can imagine with a narrower field of view, you're not seeing and detecting some of the evaporations that is occurring. And so the in vivo system, by capturing the edge of the specimen, can observe and make reactions in detection rate, for example, or laser energy, however you want to control the electric field by observing what's evaporating at the very edge. And so the DPV laser and the wide field of view improves data quality, and it means a faster time to knowledge. Ultimately, by seeing more of the specimen, we should also have an improved ability to do reconstruction because we're not making guesses at data that we can't see. We're actually able to see the data all the way out to the specimen. So just in very brief summary, the Inviso 6000 is a straight flight path system. It is not a local electrode atom probe, but rather an atom probe system with a flat counter electrode, has DPV mode operation, and has dual beam illumination to improve reconstruction fidelity because we have a more symmetric specimen. And the 6000 XR is a local electrode atom probe. It's configured with high degree of automation in it, allowing very high throughput. It also includes not just the DPV system, but also introduces voltage plus laser. So it's hybrid pulsing system that has been shown to substantially improve the data quality. So with that, thank you very much for the time and the opportunity to present this. And happy to take any questions here, or we can break for lunch.
Hey, thank you very much, Rob. Thank you. Okay, so if there's any questions. Okay, if not, I think anybody knows Rob. So if you have questions, I think you can feel free to contact Rob directly and to gain more information regarding the LEAP 6000.
It's been a quiet group today.
Yeah, right. Okay, I think we can have the lunch break now, and the afternoon session gonna be start from 1 o'clock in the afternoon Beijing time. So thank you very much, everybody. Thank you for all our speakers in this morning, and thank you for our listeners. And thank you. And
thank you for organizing.
Okay. Thank you very much, and we'll see you later. See you in the afternoon. Bye.